Welcome in. We are absolutely thrilled to have you sitting here with us today.
Yeah, you might really want to grab a coffee for this one, maybe get comfortable.
Exactly. Settle in. Because you are about to embark on an incredibly meticulous, deeply profound journey. Today's deep dive is dedicated entirely to completely deconstructing a fascinating text.
Right, it's titled Hermann Weyl and the Geometric Foundations of Gauge Theory.
And our mission for you today is simple in theory, but, well, the execution is going to be incredibly rigorous.
Very rigorous.
We are going to process this source material absolutely linearly. We're talking start to finish, leaving nothing behind.
Not a single sentence.
Right. We are not going to skip a single underlying concept or a single mathematical formula. We are going to treat this historical text with the absolute utmost respect.
Analyzing it line by line, strictly in the exact order it was written.
That is precisely the plan. To truly honor the depth of this material and to respect your time as a learner, we will operate under a specific protocol today.
We are going to assume that we have infinite time together. We will deliberately slow down our pacing.
Yeah, we won't just read the mathematics out loud.
Right.
We will digress into the foundational whys of every single theorem.
Like, why did this math need to be invented in the first place? What problem does it actually solve?
Exactly. And to ensure absolute rigor, after every single conceptual paragraph or complex mathematical step, we are going to explicitly pause.
We'll perform a strict verbal completeness check.
Right. To verify we haven't missed a single drop of insight, we want to make sure you are right there with us in the room, building this towering intellectual structure, brick by single brick.
I cannot wait to get into this.
Me neither. But before we open the book, let me just give you a tiny hook to keep in the back of your mind.
Yeah.
We're going to tease the ultimate aha moment of this source material.
Oh, this is the best part.
By the end of this deep dive, we will discover how a purely philosophical question, literally someone just sitting there wondering about the physical size of a 1-meter ruler if you magically transported it into outer space.
Say, all the way to the Andromeda Galaxy.
Right. How that bizarre question accidentally birthed the entire mathematical foundation of electromagnetism.
It is an unbelievable story.
It really is. It's about how questioning the most basic, everyday assumption of reality led to an absolute revolution in modern physics. So, looking at our parameters, does that cover the premise and the introduction of our mission today? Did I leave anything crucial out of the setup?
I think we've locked it in perfectly. The rules of engagement for our deep dive are completely set, and the destination is clear for you, the listener. Let's proceed to the first section.
Excellent. So, opening the text, it begins with a historical and philosophical anatomy of Hermann Weyl's work. The very first paragraph comes out swinging.
It really does.
It states that Hermann Weyl's creation of gauge theory completely upended 20th century theoretical physics and differential geometry.
Upended is the perfect word there.
Yeah, it goes out of its way to describe his work not just as a dry mathematical formulation, but as a philosophical manifesto. It showed how physics came to understand nature fundamentally through geometry. That wraps up the opening statement of the first paragraph. Have we fully digested the gravity of that intro?
We have, but we really need to linger on the word upended for a moment so you can truly appreciate the landscape at the time.
Please, unpack that.
Before Weyl, physics and geometry were viewed by most as entirely separate disciplines. You can think of geometry as the wooden stage, in a theater-static, unchanging, just sitting there.
Like a rigid grid.
Exactly. Physics was the play happening on that stage. You know, the actors, the drama, the movement of planets and particles.
Right.
What this opening paragraph is emphasizing is that Weyl, building on what was just starting to happen in the 1910s, made the stage itself the main character.
The stage started interacting with the actors.
It's a total paradigm shift. I think that covers the philosophical weight of the opening. Let's look at the next sentence, which dives into the specific years.
All right, let's proceed to that. The text immediately moves into the historical context, specifically the window of 1915 to 1918.
Crucial years.
Very. It reminds us that in 1915, Albert Einstein published his general theory of relativity. The text explicitly notes that Einstein explained gravity not as some invisible, magical pulling force across the void.
Which is how Newton saw it.
Right. But as the actual curving or geometric distortion of space-time itself.
Right.
And here's where our main character enters. The text states that Hermann Weyl was immediately and deeply inspired by this.
He looked at Einstein's geometry of gravity and wondered if he could create a unified field theory.
He wanted to integrate the only other fundamental force known at the time, which was electromagnetism, into this exact same geometric picture.
He wanted to explain all of nature with one single unified geometric language.
Looking at that historical jump from Einstein to Weyl, have we squeezed all the juice out of that context?
I believe we have, but it's worth highlighting the sheer ambition of that unified field theory goal for you. Put yourself in their shoes in 1918.
Okay, setting the scene.
Humanity essentially knew of exactly two fundamental forces in the entire universe. You had gravity, which holds the planets in orbit and keeps your feet on the ground.
Yeah.
And you had electromagnetism, which powers lightning storms, magnets, and light itself. Einstein successively geometrized gravity. Weyl's immediate brilliant instinct was to say,
The universe wouldn't use two entirely different mathematical languages for its only two fundamental forces.
exactly. If gravity is geometry, his gut told him electromagnetism absolutely must be geometry too. It's an incredibly beautiful, almost arrogant assumption about the elegance of nature.
That's the mindset Weyl had. We can confidently step forward to the text's explanation of his core philosophical problem.
Let's do it.
Okay, let's unpack this next section because here's where the text introduces the philosophy of scale, and it gets incredibly interesting.
It's the core of the whole thing.
The source contrasts the concept of the absolute versus the relative. It points out a hidden hypocrisy almost.
Einstein's hypocrisy, basically.
Yeah. Even though Einstein's brand new theory of relativity proved that the flow of time and the measurement of space depend entirely on the observer, meaning they are relative, Einstein still firmly believed that the scale of length was an absolute constant across the entire universe.
He couldn't let go of the rigid ruler.
Right. And the text uses a brilliant, vivid analogy to explain this. It says, imagine you take a standard 1-meter ruler from a laboratory in Seoul.
Okay, got it in my hand.
You then mathematically, carefully transport that exact same physical ruler across the universe all the way to the Andromeda Galaxy.
Passing through the gravitational fields of black holes and stars along the way.
Einstein's mathematical framework quietly assumed that when it arrived in Andromeda, it would still measure exactly 1 meter.
Which seems intuitive to us, right?
It does. But the text shows Weyl asking a devastating philosophical counter-question. If the very fabric of space itself is curved, stretched, and warped by gravity, why shouldn't the standard of length, the actual physical scale of the ruler, also stretch or shrink based on its position in that warp space?
How is it possible that the coordinate grid bends but the ruler stays perfectly rigid?
Exactly. That covers the text's breakdown of the absolute versus relative scale and that amazing Andromeda Galaxy analogy. Are there any hidden corners of that argument we should shine a light on before moving on?
No, I think the logic there is brilliantly laid out, but let's make sure you, the listener, really feel the weight of Weyl's objection. It is a profound shift in perspective.
Help us feel it.
Einstein had just spent years convincing the world that coordinates are relative, that your x and y change depending on gravity.
Right.
But he kept the measuring stick itself absolute. Weyl is essentially asking you to imagine a universe made entirely of rubber.
Okay, a rubber universe.
If the floor you are standing on is stretching, why wouldn't the tape measure you laid on the floor stretch with it? To assume the concept of 1 perfect meter is somehow completely immune to the violent curvature of the universe seemed like a hangover from the old, rigid Newtonian physics.
He was calling Einstein out.
He was. Weyl was looking at Einstein's equations and saying, you didn't go far enough. You made space relative, but you kept scale absolute. We have to break that rule.
It's a purely philosophical objection to a hidden assumption buried deep inside Einstein's math. The logic is sound. We can move on to the mathematical skeleton the text outlines next.
Let's proceed.
So, following the text strictly linearly, we reach the preliminary mathematical skeleton of Weyl's idea. The source explains that general relativity relies heavily on a mathematical machine called the Levi-Civita connection.
Which is a mouthful.
It is. Now, the text promises we will define that meticulously later, but it states the vital takeaway for right now is that this specific connection rigorously preserves length. It forces the ruler to stay the same size.
It mathematically enforces Einstein's rigidity.
Right. Therefore, the text states, to allow length to change dynamically, Weyl had to invent and introduce a brand new mathematical object into the geometry.
A completely new gear in the machine.
And the text provides the strict terminology right here. For you taking notes, he introduced the one-form famu phi sub mu.
Okay, phi sub mu.
And then the text describes this massive eureka moment, this brand new geometric one-form, this mathematical phi sub mu that Weyl invented purely to allow a ruler to change size in curved space, ended up mathematically matching exactly with something physicists already knew.
This is the mind-blowing part.
It matched the electromagnetic vector potential on mu, a submu. Just by allowing the geometry of space to change its internal scale, the exact equations of electromagnetism organically popped right out of the geometry.
Oh.
That covers the mathematical skeleton and that incredible eureka moment outlined in the introduction. Have we successfully mapped out the premise of this whole paper?
Well, we absolutely have, and you can almost feel the sheer astonishment Weyl must have felt in that moment.
He must have been floored.
It's crucial for you to realize he wasn't trying to force electromagnetism into his math. He wasn't working backward from the answer.
He was just doing philosophy.
He was just trying to fix what he saw as a philosophical flaw about rubbery space and rigid rulers. He introduced a mathematical tracker for his changing rulers, and nature rewarded him by revealing that the physical manifestation of a changing scale is the electromagnetic field.
The math of one was perfectly synonymous with the math of the other.
It's one of the most elegant discoveries in theoretical physics that establishes the grand premise of our entire deep dive. The introduction is complete.
Let's proceed to Chapter 1 of the source material, where we start building the foundational concepts from the ground up.
Lead the way.
Let's do it. Chapter 1 is titled Foundations, and the text immediately insists that before we can understand Weyl's scaling rulers, we must deeply understand the actual space in which we are doing this math.
We have to define the sandbox first.
Exactly. It explicitly and deliberately contrasts Euclidean space with manifolds. The source starts by reminding us about Euclidean space. This is the completely flat space we all learn about in high school algebra.
Graph paper, basically.
Yeah, it utilizes Cartesian coordinates, your standard rigid x, y, and z axis. The text points out that in this perfectly flat space, you can draw a vector, which it defines simply as a straight arrow, and you can freely slide that arrow around.
Just drag it anywhere on the paper.
You can move it anywhere on the graph, parallel to itself, without its length or its direction ever changing.
Because the paper doesn't change.
But the text states firmly, post-Einstein physics does not happen on a flat grid. It happens on a manifold.
Ah, the manifold.
A manifold is described here as a mathematical space that is curved globally, but appears flat locally. It gives the example of the surface of the Earth. That covers the text's initial contrast between high school Euclidean space and the concept of a manifold. Did I skip any vital context in that definition?
You hit all the structural points, but to truly adhere to our mandate of extreme granularity, let's ensure you, the listener, can visualize this deeply before we start doing calculus on it.
Good idea. Visuals are key here.
The text uses the Earth, but let's zoom in even closer. Think of a tiny ant walking on the skin of a large apple.
Okay, an ant on an apple.
To that ant, looking at its immediate surroundings, the surface looks perfectly flat. That is the flat locally part of the definition. Because it looks flat locally, the ant can draw a tiny XY coordinate grid right there on the apple skin and do normal high school geometry.
So for a tiny area, Euclidean math works fine.
Exactly. But if the ant decides to walk a long distance, it quickly realizes a problem. If it draws straight lines that are supposed to remain parallel, eventually those lines will wrap around the apple and intersect.
The grid gets warped.
The grid doesn't behave like a flat sheet of paper globally. It curves and meets in unexpected ways. That is the curved globally aspect.
Right.
A manifold is the strict mathematical formalization of this exact concept. A space where you can do flat math in the tiny neighborhood, but the overall neighborhood is warped.
If we have that visualization locked in, we can safely proceed to the next sentence, which introduces a massive complication, the tangent space.
I think we're ready for it.
And this is where the text throws a really tricky problem at us regarding vectors on these manifolds. It states very clearly, vectors are, by definition, perfectly straight arrows.
Like a literal, stiff, physical arrow.
Therefore, you cannot actually draw a straight vector directly on a curved manifold. It just wouldn't sit flush against the curve.
It would stick out.
To solve this, the text defines a new concept. It calls it the tangent space. At point P, TPM area, T sub P of M.
T sub P of M, okay.
The text asks you to imagine a perfectly flat, rigid plane that is just gently touching the curved manifold at exactly one single microscopic point. Let's call that point P.
Just balancing there.
Any vector that exists at point P must live flat upon this tangent plane, not on the curved surface itself.
Got it.
The text then asks you to imagine moving to another location, point Q. At point Q, there is an entirely separate, unique flat plane, defined as the tangent space at point Q, TTQ and T sub Q of M.
A completely different flat plane.
And here is the core fundamental problem the text highlights. Vectors at different points live in completely different, totally disconnected flat planes. That covers the text's formal definition of the tangent space and the core problem it creates. Does that accurately reflect the hurdle the text is putting in front of us?
It perfectly reflects the hurdle. But let's really make this vividly clear, because this is the stumbling block for so many people learning differential geometry.
It is a massive block. Let's break it down.
Imagine you are holding a stiff, perfectly flat piece of cardboard.
Okay, holding the cardboard.
Now press that cardboard perfectly tangent against the surface of a basketball. That piece of cardboard represents T sub P of M. You can take a Sharpie and draw your perfectly straight vector arrow on that flat cardboard.
So my arrow lives entirely on that one specific piece of cardboard.
Yes. Now, imagine a second separate piece of cardboard touching the basketball at a completely different spot, maybe near the bottom. That is T sub Q of M.
Okay, so two separate cardboards.
The text is emphasizing a brutal mathematical reality here. The arrow you drew on the first piece of cardboard literally does not exist on the second piece of cardboard.
They don't talk to each other.
They are separate dimensions of flat math. You cannot simply slide the arrow over the surface of the basketball because the two pieces of cardboard are tilted at completely different angles in three-dimensional space.
Because the basketball is curved.
Exactly. They are completely disconnected universes of flat geometry hovering over a curved world. If you want to compare an arrow on the top cardboard to an arrow on the bottom cardboard, you have a massive logistical nightmare.
The problem is beautifully stated. Let's look at how the text solves it with the necessity of parallel transport.
Let's see the solution.
I love that cardboard analogy, by the way. It makes the problem so obvious. If I draw an arrow on my cardboard, and you have your own cardboard touching the basketball an inch away...
My arrow doesn't exist for you.
Right. It's just invalid math over there. So the source text explicitly asks the natural question. How do you mathematically compare vectors in different tangent spaces?
How do you build a bridge?
To solve this dilemma of disconnected planes, the text introduces the concepts of parallel transport and a mathematical tool simply called a connection to act as the necessary bridge.
The connection.
It states that if you want to move a vector from point P over to point Q just so you can compare them, you desperately need a rigid mathematical rule.
You need instructions.
A rule for moving the arrow while keeping its essential characteristics, its length and the direction it points, as mathematically intact as physically possible while traversing the curve. That covers the text's introduction of parallel transport and the connection as the bridge. Have we thoroughly unpacked the why behind this step?
We have, and you should notice how brilliantly literal the mathematicians were when they named this. The word connection here means exactly what it sounds like.
It literally connects.
It is the mathematical machinery that explicitly connects your disconnected pieces of cardboard. Think of it as a highly complex instruction manual.
Okay.
It tells the vector exactly how to mathematically pivot, tilt, and adjust its coordinates as it slides off the cardboard at point P, travels microscopically across the curved surface of the basketball, and arrives perfectly flush onto the cardboard at point Q.
So it's translating the math as it moves.
Exactly. Without this connection, this instruction manual, taking a derivative, which inherently requires comparing the value of a vector at two adjacent points, is mathematically impossible on a curved surface.
Because you can't compare apples and oranges.
Mm.
Or cardboard and cardboard.
Right. The connection is the absolute prerequisite for doing calculus on a manifold. Let's look at the exact formal mathematical formula the text provides for this process.
Yes, looking at the text, we have arrived at our first major mathematical formula, and it's a big one.
Brace yourself.
The source introduces something called the covariant derivative, which it claims is the one true way to measure how a vector actually changes on a curved manifold. I will read the formula exactly as written for those following along.
Go for it.
It is the covariant derivative formula de Blana v mu plus gamma mu nu nu lambda v lambda nobla sub nu of v super mu equals the partial derivative sub nu of v super mu plus capital gamma super mu sub nu lambda times v super lambda.
That is a lot of Greek.
I know. I am looking at this Greek soup here. I see a nabla, which is that downward pointing triangle, and I see partial derivatives and a giant capital gamma.
It looks intimidating.
Thankfully, the text breaks down the why of this formula into a really beautiful conceptual equation. It states that the covariant derivative represents the real change of the vector.
The real change.
And it says this real change is equal to the apparent change measured by your raw coordinates, which is the partial derivative, part minus the fake change, that only happen because your coordinate axes themselves are curving under your feet.
And that fake change is handled by that massive gamma term.
Exactly. So, real change equals apparent change minus fake change. Looking at the formula and that conceptual breakdown, did I miss any crucial details from the text?
You captured the structure flawlessly, but let's take a few minutes to ensure the listener truly internalizes the difference between apparent change and real change. This is the heart of general relativity.
Please give us a mental model for this.
Imagine you are driving a car straight forward on a massive, completely flat, featureless salt flat. Your hands are perfectly steady on the wheel. You are not turning it even a millimeter.
Okay, driving perfectly straight.
Therefore, your real change in direction is absolutely zero. But now, suppose some prankster has painted your GPS coordinate grid onto the ground not as a square grid, but as a giant swirling spiral.
Oh, that's deeply confusing.
Right. As you drive perfectly straight, you are constantly crossing those painted spiral lines at different changing angles.
Because the lines are curving, not me.
Exactly. If a computer was naively looking only at your GPS coordinates, which represents taking only the standard partial derivative, it would see your angle relative to the grid lines constantly changing. The computer would falsely calculate that you are turning in a massive circle.
But I'm not turning.
You aren't turning. The grid is turning. That connection term in the formula, that capital gamma, is the mathematical program that calculates the fake turning caused by the spiral grid itself and forcefully subtracts it out of the equation.
It filters out the illusion.
Precisely. Once it subtracts the fake turn from the apparent turn, you are left with the covariant derivative, your true, real change, which correctly shows you are driving perfectly straight.
It separates the movement of the object from the warping of the stage. The formula makes perfect conceptual sense now. Let's zoom in on that gamma term specifically, as the text dictates.
Let's dissect the gamma.
I love that. The math is literally filtering out the optical illusion of the curved grid. So, following the text, it specifically zeroes in on this exact gamma term we've been talking about.
It gets a formal name.
Yes. It formally names it the Levi-Civita connection, or Christoffel symbol. Gamma mu nu lambda, capital gamma supermus sub nu lambda.
Christoffel symbol.
The text asks the fundamental question, what does this physically mean? And it answers by calling the Christoffel symbol the mathematical blueprint of how the basis vectors, meaning the actual coordinate axes themselves, twist, turn, and scale as you take tiny steps through the space.
It's the blueprint of the twist.
It dictates exactly how much a vector will appear to change simply because the space underneath it is curving. That covers the text's specific analysis and naming of the Christoffel symbol. Is there any deeper mathematical nuance buried there that we need to excavate?
I think we've dug up the core meaning perfectly. If you want a visual for the Christoffel symbols, think of them as the localized curvedness data for any given millimeter of the manifold.
So it changes depending on where you are?
Absolutely. It is a specific set of numbers that tells you exactly how much your tangent cardboard is tilting, pitching, and yawing as you take a microscopic step in the x direction, or the y direction.
It's the local weather report for curvature.
That's a great way to put it. It is the raw geometric DNA of the curvature at that exact point. If the space is flat, like high school geometry, all the gamma terms are just zero.
Because there's no fake change.
Right. If the space is highly curved, like near a black hole, these numbers become extremely large and complex. It's the ultimate instruction manual we mentioned earlier.
And with that foundational piece secured, the text transitions us into Chapter 2, where we actually learn how to calculate this blueprint. Are we clear to move on?
The foundation is set. Let's proceed to Chapter 2.
Which brings us right into Chapter 2, Riemannian Geometry and the Levi-Civita connection. The text kicks off this chapter by defining what it calls the absolute fundamental ruler of spacetime.
The most important object in the room.
It formally names this ruler the metric tensor d mu nu sub mu nu.
G sub mu nu. Okay.
Right after naming it, it provides the core mathematical formula for how this tensor actually measures distance across a curve.
A line element.
The formula is the metric line element dx mu dx nu ds squared equals g sub mu nu times dx vog dx super nu.
A classic equation.
Now, the text explicitly stops us here and demands that we explain a very specific piece of formatting used in this formula called the Einstein summation convention.
Ah, the famous convention.
It notes that if you look closely at the math, the indices mu and nu appear twice, once as subscripts on the g and once as superscripts on the dx terms. The text explains that because they appear twice like this, the summation symbols, those giant Greek sigma symbols you usually see in calculus, are completely omitted for brevity.
They're just invisible.
But we are actually meant to be summing up all these tiny distances over all possible dimensions of the space. That covers the definitions of the metric tensor, the line element formula, and the explanation of the summation convention. Have we satisfied the text requirements for this paragraph?
We have, but we really need to linger on the concept of the metric tensor for you because it is the undisputed star of the show.
Okay, let's put it in the spotlight.
We talked earlier about the manifold being the empty, curved wooden stage. If that's the case, the metric tensor is the heavy grid of tape measures laid out across the floor of that stage.
So it's the physical measuring device.
It is a mathematical matrix. You feed it two tiny microscopic directional steps, say a step in the x direction and a step in the y direction, which are the dx supermu and dx supernu terms.
You plug those into the matrix.
The metric tensor chews on those directions, accounts for the curvature of the floor, and spits out the absolute physical distance squared between them.
Wow, so it does all the heavy lifting.
It really does. In flat Euclidean space, this entire fancy metric tensor formula collapses down perfectly into a squared plus b squared equals c squared.
Wait, really? It's just the Pythagorean theorem?
It is literally just the Pythagorean theorem in disguise. But in curved space, those tape measures are stretching and compressing depending on where you are, so the G sub mu nu matrix tells you exactly how much they stretch.
That makes so much sense.
And as for that Einstein summation convention, there's a famous bit of history there. Einstein reportedly joked later in life that it was his greatest singular contribution to mathematics.
Not relativity, but the summation shortcut.
Yes. Simply because by inventing the rule that repeated indices mean you add them up, he saved his own hand from having to write the Greek sigma symbol literally thousands of times while drafting general relativity.
That is hilarious. Just pure laziness leading to genius.
It's a pure, beautiful mathematical shortcut. We understand the metric. Let's proceed to the two grand principles of Riemannian geometry that govern how this metric behaves.
I love that the guy who revolutionized our understanding of time and space was mostly just trying to save chalk and avoid hand cramps.
History is funny like that.
So moving forward, the text presents what it calls the two grand principles of Riemannian geometry. It explicitly states that these two principles are absolutely vital because together they uniquely and perfectly determine the exact formula for the Levi-Civita connection we've been talking about.
They set the rules of the game.
The first principle is called Principle 1, metric compatibility. The text provides the very short formula for this. The metric compatibility condition nabla vector sub lambda of G sub mu nu equals 0.
Short but powerful.
The text explains the deep underlying philosophy of this tiny equation. It mathematically guarantees that the fundamental ruler never changes its absolute size, and the angles between vectors never arbitrarily distort as you parallel transport them across the space.
The ruler is secret.
The text also includes a crucial, bolded foreshadowing note right here. It explicitly reminds us that this exact rule, this metric compatibility, is the very principle that Hermann Weyl is going to intentionally shatter into pieces later on in Chapter 3.
Spoilers.
Right. That covers the text presentation of the first principle. Have we captured the essence of metric compatibility?
Perfectly captured. But let's translate that short mathematical sentence into English for you. It says, the covariant derivative of the metric tensor equals 0.
Okay, translating the Greek.
Remember our definition of the covariant derivative. It means real change. So this formula literally says, the real change of the tape measure is exactly 0.
It does not stretch, period.
It means the absolute rulerness of the ruler is sacred. As you slide your tangent cardboard across the curved basketball, the underlying definition of what constitutes a physical millimeter does not mutate.
This was Einstein's hill to die on.
It was Albert Einstein's foundational assumption about reality. A standard meter is exactly 1 meter, whether it is floating in the empty, flat void of deep space or sitting on the unimaginably dense, violently curved surface of a neutron star. The geometry bends, but the ruler stays rigid.
It's such a firm stance.
Keep that locked in your mind, because as the text warns, Will is coming for that assumption. Let's look at the second principle.
Right. It feels like we're setting up the rules just so we can break them. Moving to Principle 2, the text labels it the torsion-free condition.
Torsion-free.
The formula provided is the torsion-free condition gamma lambda nu mu. Capital Gamma super lambda sub mu nu equals capital Gamma super lambda sub nu mu.
So it's symmetric.
Exactly. The text explains the geometric reality of this condition. It states that if you take two vectors and use them to draw a parallelogram, by taking the first vector and parallel transporting it along the second, and vice versa, a torsion-free space mathematically guarantees that the parallelogram will perfectly, seamlessly close without any weird gaps appearing at the corner.
The corner's touch.
Mathematically, it means the connection term is perfectly symmetric regarding its lower indices. Swapping mu and nu doesn't change the outcome. That covers the second principle. Does that fully satisfy the text's explanation of a torsion-free space?
It does, but torsion is a deeply weird and fascinating concept that deserves a moment of your attention.
Please, explain torsion.
Imagine you are walking in a city grid. If the space has no torsion, walking one block north, then turning and walking one block east puts you on the exact same street corner as if you would walk one block east first and then one block north.
The paths close. The parallelogram connects.
Right, but if a space actually has torsion, the space itself intrinsically twists. Walking north then east puts you in a completely different physical and mathematical location than walking east then north.
Oh, that would be a nightmare to navigate.
The space essentially twists back on itself like a spiral staircase. By mathematically enforcing this symmetry, by definitively declaring that the gamma with a mu subscript is completely identical to the gamma with a nu subscript, Riemannian geometry strictly outlaws this twisting.
It outlaws the spiral staircase.
It demands that the parallelogram of space-time must seamlessly close. No Escher painting paradox is allowed.
So we have our two principles. The ruler doesn't change, and the space doesn't twist. Let's proceed to the massive derivation section where the text combines them. Are we ready for the heavy math?
We are ready. Let's proceed.
Okay, brace yourselves, because the text warns us this is an incredibly dense section. We are now instructed to meticulously execute what the author calls the four-step mathematical magic.
Magic is a strong word, but it fits.
The goal here is to derive the exact formula for the Levi-Civita connection directly from nothing but the metric tensor.
Just from the tape measure.
Step 1 commands us to expand the metric compatibility principle we literally just discussed. We take the metric compatibility condition navalanda lambda g sub mu nu equals 0, and we are told to write out its full expansion by plugging in the long covariant derivative definition we learned back in Chapter 1.
We're unpacking the box.
The text then instructs us to use basic algebra to move the partial derivatives over to one side of the equal sign. This results in a new equation the text labels Equation A.
Equation A.
Equation A essentially states that the partial derivative of the metric tensor is equal to the sum of two distinct terms, both of which contain the Christoffel connection multiplied by the metric tensor. That covers Step 1, the expansion of metric compatibility. Did I rush through any of that algebraic setup?
No, you tracked the logic perfectly. But
Yeah.
let's pause and appreciate the strategic necessity of what the text is doing here. Think of it as a rescue mission.
A rescue mission. Who are we rescuing?
Our ultimate goal is to find the exact formula for the connection, the gamma terms. But right now, those gamma terms are trapped. They are buried deep inside the covariant derivative formula, inextricably tangled up with the partial derivatives and the metric.
They're locked inside the equation.
Step 1 is the algebraic equivalent of taking a hammer and cracking open the shell.
Ah,
By explicitly expanding the formula and forcefully isolating the partial derivative on the left side of the equal sign, we have exposed the raw, vulnerable gamma terms on the right side.
we pulled them out of hiding.
They are out in the open, but they're still multiplied by the metric. We are setting the stage to completely isolate them. Let's look at how Step 2 accomplishes this with a very clever trick.
Right, Step 2 is titled the index permutation trick. And the text actually stops and demands we explain the exact why behind this specific trick before doing it.
We can't just do math without knowing why.
It explains the core algebraic problem. Right now, we only have one single equation A, but it has multiple different unknown gamma terms inside of it. From basic high school algebra, we know that to solve for multiple unknown variables, you need a system of multiple equations.
Specifically, 3 equations for this problem.
Therefore, the text instructs us to take equation A and perform a cyclic permutation on the indices lambda, mu, and nu.
A cyclic permutation.
It says we create a second equation simply by swapping lambda for mu, mu for nu, and nu for lambda, to shifting them all one seat to the right. Then we create a third equation by cycling them one more time. We now possess 3 slightly different but perfectly valid versions of equation A. That covers Step 2, the index permutation trick. Does that algebraic strategy make sense?
It makes perfect sense, and it is a vital tool for you to understand in tensor calculus. You can visualize this trick by imagining you are holding a complex three-dimensional geometric sculpture.
Okay, looking at the sculpture.
The core physical geometry of that sculpture hasn't changed at all, but by swapping the labels of our dimensions, by playing a game of musical chairs with the x, y, and z indices, or in this case, lambda, mu, and nu, you are essentially rotating the sculpture and looking at it from three entirely different mathematical angles.
So we're just walking around the object, taking different pictures.
Exactly. By looking at it from three angles, you actively generate three distinct mathematical statements about how the metric changes across the space. You haven't added any new physical data, but you've reorganized the existing data into a system of three equations.
That is so clever.
This is a classic, incredible, powerful technique used constantly in advanced physics to generate enough independent equations to systematically hunt down and isolate a target variable. And our target is the gamma. Let's proceed to step 3, where the hunt comes to an end.
Okay, step 3 is simply titled Combine and Cancel. The text instructs us to take our newly generated system of three equations and combine them.
Mash them together.
Specifically, we must add equation 1 and equation 2 together, and then we strictly subtract equation 3 from that combined total.
Okay, addition then, subtraction.
The text then requires us to explicitly walk through the resulting algebraic cancellation. It points out that when we do this addition and subtraction, we end up with a massive string of terms.
Just a huge mess on the page.
However, by utilizing two things we already proved, the symmetry of the metric tensor, where G sub mu nu is identical to G sub nu mu, and the symmetry of the torsion-free connection we established in Principle 2, a truly beautiful mathematical cancellation cascades through the equation.
It's like dominoes falling.
Positive terms perfectly match with negative terms. 6 complex terms on the right side of the equal sign completely condense down, mathematically annihilating each other perfectly until only a single fully isolated connection term survives the carnage, multiplied by a simple factor of 2. That covers step 3, combine and cancel. Did I accurately describe that algebraic bloodbath?
You did, and it truly is a moment of profound mathematical elegance. It's the payoff for all the hard work you've done so far. You start with this massive, intimidating, sprawling string of complex terms.
It looked unsolvable.
But because we explicitly demanded philosophically that the space be torsion-free in Principle 2, the math obeys. The twist represented in one direction perfectly and exactly annihilates the twist in the opposite direction.
The symmetry saves us.
The negative terms that we generated by subtracting that third equation act like a laser-guided missile. They specifically target and take out the duplicate symmetrical terms from the first two equations. All the noise, all the redundancy completely vanishes.
It just wipes the board clean.
You are left with a pristine, totally uncluttered mathematical relationship. Just partial derivatives on one side and a single surviving gamma term on the other. It's beautiful.
Mm-hmm.
Let's proceed to the final step. Step 4, to clean it up.
Right, we are almost at the finish line for this derivation. Step 4 is titled the inverse metric.
The final touch.
We now have an equation with our sole surviving connection term on one side, but it's currently bogged down because it's being multiplied by a metric tensor and there's a factor of 2.
We need it completely alone.
The text instructs us to clear this out by multiplying both sides of the entire equation by the inverse matrix of the metric tensor, which is strictly written as G with superscript indices instead of subscripts.
Inverse matrix multiplication.
The text pauses to explain the matrix algebra here. It states that multiplying any matrix by its own inverse creates the Kronecker delta function. In tensor calculus, this delta function acts exactly like an identity matrix. It effectively equals 1, and its primary job is to mathematically alter the indices, perfectly and completely isolating the Christoffel symbol all by itself.
So it just pops it right out.
We divide by 2 and we are done. And now, the strict protocol of our deep dive requires I read the final, majestic, hard-won result of this derivation out loud.
Let's hear it.
The Levi-Civita connection gamma lambda 1, partial mu rho nu, capital gamma super lambda sub mu nu equals 1/2 times g super lambda rho, multiplied by the quantity. The partial derivative sub mu of g sub nu rho plus the partial derivative sub nu of g sub mu rho minus the partial derivative sub rho of g sub mu nu.
Wow.
Yeah, wow. That covers step 4 and the triumphant final derivation of the Levi-Civita equation. Have we thoroughly completed the 4-step magic?
We have completed it flawlessly. And I really want you to take a moment, sit back, and appreciate exactly what you have just achieved by following the logic of this text. It is a monumental result.
It feels monumental.
You have definitively proven that if you only know one thing about a universe, if you only have the metric tensor, the fundamental tape measure of the space, you can perfectly, mathematically calculate exactly how that space curves and exactly how vectors must twist and turn when they move through it.
You don't need any outside information at all.
None. You take the partial derivatives of the tape measure, you mix them together by adding 2 and subtracting 1, you multiply the whole thing by the inverse of a tape measure, and out pops the exact blueprint of space-time curvature.
It's like magic.
This is not just abstract math. This is the exact, literal mathematical machinery that Albert Einstein used to calculate the anomalous orbit of the planet Mercury. It is the exact formula he used to predict the bending of starlight around the sun. You're looking at the engine of general relativity.
That is chilling, honestly.
But looking at an engine is different than turning it on. Let's proceed to the next section, where the text forces us to apply this massive theory to a concrete, visualizable reality.
I am so ready to turn the engine on. We are moving into the second half of Chapter 2, titled The 2D Polar Coordinate Example. The text explicitly states that leaving the math abstract is not enough. We must apply this theory to a tangible reality to make it concrete.
We have to test drive it.
It introduces a very specific real-world math problem for us to solve together. It commands us to find the exact connection term, the Christoffel symbol for the radial direction, capital gamma super r sub theta theta, for a specific flat space defined by the polar coordinate metric ds22 plus r2 d theta 2s squared equals dr squared plus r squared times d theta squared. That covers the setup and introduction of the specific polar coordinate problem. Are we clear on the mission parameters for this example?
We are entirely clear. But let's demystify what the text is actually doing here for the listener. It is purposefully taking us down from the intimidating, four-dimensional abstract realm of black holes and general relativity and placing us onto a completely flat, simple two-dimensional piece of paper.
Just a flat piece of paper. Okay.
However, there is a catch. Instead of using a standard XY grid, like a city street grid, we are using polar coordinates. Polar coordinates describe a location not by going over x and up y, but by stating a radius, how far out from the center you are, which is r, and an angle, how far you rotate around the center, which is theta.
Think of a radar screen sweeping around.
Exactly. Now, even though a piece of flat paper has absolutely zero intrinsic curvature, it's not a basketball, the coordinates we are using to draw on it are curved. They are made of concentric circles and outward pointing rays.
Because we chose to draw them that way.
Right. Therefore, recalling what we discussed way back in Chapter 1 about driving on the spiral GPS grid, there will be a fake change when moving vectors around this paper. And because there is a fake change, our Christoffel symbols will absolutely not be zero.
The math will pick up on the spiral grid.
We have to use the massive Levi-Civita formula to calculate exactly what they are. Let's proceed to the text's execution of the first 3 steps.
Okay, let's fire up the Levi-Civita machine. The text outlines the solution in very methodical execution steps. Steps 1 through 3 are basically just gathering our material.
Prepping the ingredients.
First, we define our coordinates explicitly. X superscript 1 is going to be the radius, r, and x superscript 2 is going to be the angle, theta. Second, the text tells us to extract the metric tensor matrix directly from our given line element formula. Looking at the formula, the coefficient standing next to the dr squared term is just an invisible one. So the matrix component g sub r strictly equals 1. The coefficient standing next to the d theta squared term is r squared. So the matrix component g sub theta theta equals r squared. Third, we have to calculate the inverse matrix because the Levi-Civita formula demands it. The text points out that because this is a simple diagonal matrix with no cross terms, calculating the inverse is incredibly easy. We just take the mathematical reciprocal.
Just flip them over.
So the inverse g super rr is simply 1 over 1, which is 1. And the inverse g super theta theta is 1 over r squared. That covers execution steps 1 through 3. Did I gather the materials correctly?
You gathered them perfectly, and you are carefully and methodically building the exact mathematical components needed to feed the big formula. You have your metric, which is the tape measure specifically designed for polar coordinates, and you have its exact mathematical inverse.
They are locked and loaded.
I want you to notice something incredibly profound buried in those simple components. Look at the metric term for the angle, the g sub theta theta, which equals r squared. It explicitly depends on r.
It depends on the radius.
Yes. This perfectly matches physical reality. If you are standing 1 foot from the center of a circle and you rotate 10 degrees, you only walk a tiny distance.
Barely a step.
But if you are standing a mile away from the center and you rotate that exact same 10 degrees, you walk a massive physical distance. The size of the angle ruler inherently depends on how far out you are.
The ruler stretches the further out you go.
This dependency on position, the fact that the ruler changes based on r, is exactly what creates the partial derivatives that generate the non-zero connection terms. The math knows about the geometry. Let's proceed to actually plugging these components into the Levi-Civita formula in steps 4 through 6.
Right. Here is where we earn our keep. Moving to execution steps 4 through 6. The text tells us to take our gathered components and plug them mercilessly into that majestic, massive Levi-Civita formula we derived earlier.
Into the machine they go.
Remember, the specific target the text gave us is to solve for gamma super r sub theta theta. The text walks us through taking the 3 partial derivatives required by the formula. It points out a massive shortcut.
Oh, we love a shortcut.
Most of the terms evaluate immediately to 0. Why? Because the metric component, g sub rr, is just the constant number 1, and the derivative of a constant is 0.
They just vanish.
The text shows that the absolutely only surviving partial derivative in the entire massive bracket is the derivative of the g sub theta theta component, which we know is r squared taken with respect to the radius r.
It's the only one left standing.
The text explicitly calculates this out for us. From basic calculus, the derivative of r squared with respect to r is simply 2r.
2r.
Finally, we plug that 2r back into the main formula. We multiply it by the negative sign that exists inside the formula's brackets, and we multiply it by the 1/2 sitting at the very front of the formula.
The 1/2 from earlier.
The 2 from the 2r and the 1/2 perfectly cancel each other out. The text then presents the final calculated mathematical result. The answer for the connection is simply negative r. That covers execution steps 4 through 6 and the final calculated result of negative r. Did the algebra hold up under scrutiny?
It held up beautifully. The algebra collapses with incredible elegance. Out of that massive, intimidating, sprawling formula with multiple interacting partial derivatives, for this specific, simple flat space described by polar coordinates, all the noise vanishes. Everything zeroes out except that single, lonely term.
It's astonishing how clean it is.
The cold, hard math dictates that the connection, the twisting blueprint of the space for a movement involving 2 angle steps, theta, that affects the radial direction r, is strictly and simply negative the current radius.
Negative r.
But as any good physicist will tell you, a negative letter on a piece of paper is just a number. It isn't physics until you interpret it. Let's proceed to the most important part of this entire example. The text's aha interpretation of what negative r actually means in the real world.
I was waiting for this. The text literally demands we ask the question, what does this minus r actually mean?
Yeah.
And it provides the most satisfying interpretation.
Lay it out for us.
It explains it like this. Imagine you have a vector. That vector is pointing perfectly sideways, exactly along the circular angular direction, theta. Now imagine you try to physically move that vector forward along that circular path.
Moving it around the radar screen.
The connection math we just calculated dictates that the vector will inevitably experience a fake change. This fake change will actively pull the vector inward. How do we know it's inward? Because the result we got was a negative sign attached to the r direction.
Right, because positive r is outward.
The positive r direction is outward away from the center, so negative r means it strictly pulls toward the center. The text then enthusiastically reveals the punchline. This abstract mathematical term, derived purely from the geometry of a metric tensor, is the exact geometric manifestation of centripetal force.
It's just brilliant.
It is the underlying math unequivocally proving that in order to move an object in a circle, you must constantly, continuously be accelerating it, pulling it toward the center. That covers the text's interpretation of the result as the emergence of centripetal force.
Did I land the punchline correctly? You landed it flawlessly. And this is a truly spectacular payoff for you as a learner. Think about the journey you just took. You started with the hardcore, highly abstract machinery of Albert Einstein's general relativity metric tensors, index permutations, covariant derivatives.
Really heavy stuff.
You took that massive machinery and you applied it to a completely mundane, flat piece of paper drawn with circular coordinates. And what happened?
The math just spat out the physics.
The math, autonomously, without any prompting from Newtonian physics, organically generated the fundamental concept of centripetal force. It showed you definitively that geometry dictates dynamics. If your chosen path is a circle, the underlying geometry physically forces the existence of an inward-pointing vector.
It proves that the Levi-Civita machinery works flawlessly.
It is a perfect, internally consistent mathematical universe, which makes what happens next so dramatic. Let's proceed to Chapter 3, where Hermann Weyl looks at this perfect, beautiful machinery and intentionally decides to break it.
Enter the rebel. Chapter 3 is titled Hermann Weyl's Revolution, and the very first subsection is appropriately named Breaking the Rules.
He breaks them.
The text aggressively returns us to Weyl's profound philosophical crisis from 1918 that we talked about in the intro. It demands we rigorously deconstruct his objection to Einstein's assumption of a global scale.
The Andromeda ruler problem.
The text points out again that Einstein strictly enforced the metric compatibility principle, the ironclad mathematical rule that a ruler fundamentally never ever changes size anywhere in the universe. Its covariant derivative is zero.
The rigid tape measure.
But Weyl strongly objected. He argued that if Einstein has already proven that the direction of vectors is relative, and that the coordinate grid is deeply warped by local gravity, it is philosophically inconsistent, almost cowardly, to insist that the length of those exact same vectors remains an absolute, rigid, global constant.
It's a half measure in his eyes.
He firmly decided that true relativity must mean relativity of scale as well. And therefore, the text states, he mathematically decided to shatter the rule of metric compatibility. That covers the text revisiting Weyl's philosophical crisis and his decision to break the fundamental rule. Have we fully captured Weyl's motive here?
We have, and you really have to pause and appreciate the sheer intellectual audacity of Hermann Weyl in this moment. Think of the context. He is looking directly at Einstein's masterpiece, general relativity.
The most famous theory in the world.
This is a theory that had literally just stunned the entire scientific world by correctly predicting the exact degree to which starlight would bend during a solar eclipse. Einstein was a global icon. General relativity was considered perfect.
Untouchable.
And Weyl looks at it and says, it's mathematically beautiful, Albert, but it is philosophically flawed. He fundamentally believed that a true theory of relativity must be completely 100% local. Nothing, absolutely nothing, should have a fixed universal scale dictated from on high.
He couldn't accept the absolute ruler.
To Weyl, the idea of an unchanging, rigid standard ruler was a relic of classical Victorian-era thinking, trying to sneak its way into a modern relativistic universe. He couldn't abide it. So, he broke the fundamental principle of Riemannian geometry. Let's proceed to examine exactly how he mathematically modeled this rule-breaking via the concept of scale invariance.
The text immediately moves to explain this mathematical modeling under the heading scale invariance, or, as the text notes Weyl originally called it in German, Eichenvariance.
Eichenvariance, yes.
The text notes this later became famously known in modern physics as gauge transformation. The source provides the crucial defining formula for this transformation, and I am required to read it precisely as written.
Let's hear the formula that broke the rules.
The gauge transformation formula, don't need x, read as sub nu and x, write x g sub nu of x, transforms to tilde g sub nu of x equals e to the power of 2 sigma of x times g sub nu of x.
There it is.
Now, the text is incredibly meticulous here. It doesn't just throw the formula at us. It demands we explain the specific why of this exact mathematical format. Why these specific symbols?
Every symbol was chosen for a reason.
First, it asks, why use an exponential function, e to the power of? The text explains the physical logic. Lengths and scales in the real world must always be strictly positive numbers. You absolutely cannot have a real physical ruler with a negative length.
It makes no physical sense.
By putting the scaling function sigma into an exponent, the math guarantees the result will always be positive, preserving physical reality.
Because e to any power is always positive.
Second, it asks, why is there specifically a factor of 2 sitting up there in the exponent? The text explains that because the metric tensor g sub mu nu fundamentally measures length squared, as we clearly saw earlier in the line element ds squared, the arbitrary scaling factor must also be squared to keep the units balanced.
Keep the math legal.
In the mathematical rules of exponents, squaring a function is perfectly identical to multiplying its exponent by 2. That completely covers the scale invariance gauge transformation formula and the meticulous mathematical why behind its specific structure. Did I properly decode Weyl's scaling formula?
You decoded it perfectly. And what you are looking at is one of the most important equations in the history of physics. This transformation formula is Hermann Weyl mathematically stating to the universe, I demand the right to stretch or shrink the space-time measuring tape at any localized point x by any arbitrary random amount defined by my new function sigma, and I demand that the fundamental laws of physics do not break when I do this.
It is an incredible demand to make of the universe.
It is a stunning requirement. By using the smooth, always positive exponential function, he ensures the math remains completely well-behaved, there will be no fatal division by zero, and no sudden, impossible negative distances appearing in the geometry.
It's controlled chaos.
He is rigorously formalizing the concept of a completely elastic universe where scale is nothing more than a local convention, no more absolute than choosing to measure in inches instead of centimeters. But, as the text is about to show us, you cannot just break a fundamental mathematical rule like metric compatibility without severe consequences.
The universe pushes back.
Let's proceed to see exactly how Weyl was forced to fix the mathematical chaos he just intentionally created.
The text immediately addresses this exact consequence. It points out that because Weyl broke metric compatibility, the length of a vector is no longer stable. It now changes arbitrarily as you move it around the manifold.
It's stretching and shrinking wildly.
If the scale of reality is now changing unpredictably in the XYZ and time directions based on that arbitrary sigma function, you desperately need a mathematical way to track that chaotic localized change. Otherwise, calculus becomes impossible again.
You lose the ability to do math.
The text states that Weyl realized he absolutely needed to invent a brand new geometric field to track how the scale shifts from point to point. And here, the text formally reintroduces the mathematical object we teased all the way back in the introduction.
Here it comes.
The one-form fimu fishiabu.
A one-form.
The text declares that this new geometric field exists entirely and only to absorb, counteract, and strictly catalog the dynamic changes in the length of the ruler as it moves through this new elastic space-time. That covers the necessary introduction of the one-form as the official tracker for scale change. Does that accurately describe the job description of Fishibu?
It perfectly describes its job. And for you listening, this is the absolute crux of what gauge theory actually is. This is the big secret of modern physics.
The big secret. Let's hear it.
When a theoretical physicist demands a new symmetry, in Weyl's case, he demanded the freedom to arbitrarily change the geometric scale locally without breaking the underlying physics. The rigid mathematics forces you to pay a price.
A mathematical toll.
To maintain balance, the math literally forces you to introduce a brand new compensating field to keep the equations balanced. The scale of the universe might shrink wildly over here and expand dramatically over there, but this newly invented one form, this phi sub mu, acts as the ultimate, perfectly accurate accountant.
It balances the books.
It perfectly tracks every single expansion and contraction, subtracting them out of the derivative so that the underlying physical laws remain smooth and consistent. The symmetry demands the field. It's a profound realization.
It really is.
Let's proceed to the grand finale of the source text, which deeply analyzes the actual visualizable geometric nature of this accounting field, this one form.
Which brings us directly to the final analytical section of our source text, wonderfully titled Vectors versus One-Forms. The text demands we draw a deep visual contrast between these two mathematical objects to truly understand Weyl's achievement.
Visuals are so important here.
It starts by reminding us about vectors. A contravariant vector, denoted as v superscript mu, is easy to visualize. As we discussed, it is simply an arrow. It represents movement, velocity, or a push across the space.
Just a straight arrow.
But then, the text provides a stunningly beautiful, almost poetic geometric visualization for the covariant vector, which is our one form, phi sub mu. It states explicitly that a one form is not an arrow. You must not visualize it as pointing somewhere.
Throw the arrow out.
Instead, the text visualizes it as a series of parallel contour lines, or a layered topological density woven across the space itself.
Contour lines.
The text describes the one form as a mathematical machine. The interaction works like this. You feed a vector arrow into this one-form machine, and the machine outputs a specific number. That number represents exactly how many of those contour lines the vector physically pierced through.
It counts the piercings.
That covers the text's deep contrast between contravariant vectors and one-forms and the beautiful geometric visualization of the one form as a density of contour lines. Have we squeezed every last drop of nuance out of the final sentence of this source text?
We have thoroughly, completely unpacked it. And this final visualization is absolutely essential for you to carry away from this deep dive.
Yeah.
I want you to imagine a topographic map of a massive, rugged mountain.
Okay, looking down at a topo map.
The vector, the arrow, represents the exact path you are hiking. It has a direction and a length. The one form, phi sub m, represents the elevation contour lines drawn directly onto the map.
Those squiggly circles.
The steeper the side of the mountain, the denser and more tightly packed those contour lines are. When your vector path crosses those lines, the mathematics simply calculates how much your elevation, or in Hermann Weyl's specific case, how much your scale, has changed during your hike.
It's just counting the lines you crossed.
And here is the breathtaking conclusion Weyl reached. He looked at the math of his contour line 1 form, this phi sub mu that he invented purely to track the stretching of a rubbery universe.
Right, his accounting machine.
And he proved that the mathematics of these contour lines perfectly, exactly, without a single missing variable, matched the known mathematics of the electromagnetic vector potential.
The aha moment.
The density of Weyl's geometric contour lines corresponded exactly, identically, to the physical strength of an electric or magnetic field in the real world.
That is unbelievable.
He proved that electromagnetism isn't some invisible magical fluid filling up empty space. It is simply the geometric manifestation of the universe constantly adjusting its own internal scale from point to point.
It's just geometry.
It is an absolutely breathtaking intellectual achievement. It unites the geometry of the void with the light shining through it. And with that realization, we have now processed every single line, every concept, and every formula of the source material.
We have indeed. What an absolute marathon, and what a massive journey this has been for us and the listener. Let's take a breath and try to synthesize everything we've meticulously unpacked over the last hour.
It's a lot to take in.
We started with a purely philosophical, almost childlike question about the fundamental nature of reality. If I take a 1-meter wooden ruler and fly it across the void of the Andromeda Galaxy, does it mathematically stay the exact same size?
Einstein, for all his revolutionary genius, assumed yes.
Hermann Weyl, armed with nothing but philosophical conviction, dared to say no. To prove his point, we had to travel with him through the grueling foundational mathematics of curved spaces. We explored manifolds, visualizing flat cardboard tangent spaces, balancing precariously on curved basketballs.
We built the foundation.
We broke down the covariant derivative, learning how the Levi-Civita connection acts as a filter, meticulously separating true, real movement from the fake, optical illusion twisting of curved coordinates.
Real change equals apparent change minus fake change.
We ground our way through the massive 4-step mathematical magic, permuting indices and canceling terms to systematically derive the exact blueprint of space-time from nothing but a matrix of tape measures. We even proved that the machinery worked flawlessly by mathematically conjuring the reality of centripetal force out of simple polar coordinates.
Which was so satisfying.
And finally, we watched Weyl shatter the golden rule of metric compatibility. By allowing the universe's scale to warp, and by introducing a one-form made of contour lines to act as the accountant tracking that warping, he achieved something miraculous.
The ultimate payoff.
He proved that the purely geometric distortion of scale was mathematically identical to the physical force of electromagnetism. He completely united the geometry of space with the physics of light.
That is a magnificent, perfect summary. It captures the exact linear progression of the logic we just deconstructed, from philosophy to mathematics to physics.
But I have to ask on behalf of the listener, why should you care? Why do we just spend all this time painstakingly dissecting century-old tensor calculus?
Because it's the foundation of everything.
Because every single time you open a newspaper or a science blog and hear a story about modern physics, whether it's about the Large Hadron Collider discovering a brand new exotic particle, or physicists debating the standard model of quantum mechanics, or humanity's ultimate desperate pursuit of a theory of everything, you need to know that this specific text is the literal ground floor.
It is the bedrock.
The concept Weyl invented here, gauge theory, the fundamental idea that demanding a local symmetry in the math actively forces a physical interacting field into existence to balance the books, is the exact mathematical blueprint used by theoretical physicists today to describe the strong nuclear force that holds the quarks inside your atoms together and the weak nuclear force that causes the sun to burn via radioactivity.
It applies to the other forces, too.
Weyl's purely philosophical insistence on local scale invariance birthed the framework for almost all of modern theoretical physics. It all started because one man simply refused to believe a ruler had to stay the same size.
Precisely. It is the ultimate testament to the power of pure thought. It demonstrates that the most complex, world-altering mathematical physical theories often stem simply from deeply, rigorously questioning our most mundane, everyday assumptions about how reality is structured.
And so, we leave you with a final provocative thought. Something for you to mull over that extends far beyond the text we analyze today.
Let's hear it.
Hermann Weyl definitively proved that if you allow the scale of physical space to be relative and redefined locally, the mathematics organically generates the force of electromagnetism to compensate. The physical force is merely a consequence of the geometry of measurement.
The math demands the force.
So what other fundamental forces might just be a trick of perspective if we redefined how we measure time locally, minute by minute, point by varying point, instead of space?
Oh, that's interesting.
Or, moving into the bizarre realm of quantum mechanics, if we completely redefined how we measure the probability of quantum states depending on exactly where and how we look,
What fields would pop out?
what hidden, currently unknown forces of nature might suddenly appear in our equations to balance those new books? Is reality, with all its varied forces and zoo of subatomic particles, ultimately just a shadow cast by the geometry of how we humans choose to measure it?
That is a truly profound question to end our deep dive on. It implies that at its deepest level, physics might not be the study of the universe at all, but rather just the study of our own measurement devices.
Thank you so much for sitting down and joining us on this incredibly deep, meticulous, and unabridged journey today. We sincerely hope your perspective on the universe and the elegant math that describes it has been fundamentally shifted. Keep questioning your world, keep looking closely at the foundations, and never ever assume the ruler stays the same size. Goodbye. Welcome to the Deep Dive. If you are listening to this right now, it means you have an insatiable curiosity about the very fabric of reality. You aren't just looking for surface-level summaries or, quick trivia. You want to understand the foundational bedrock of how the universe actually operates.
You want to see the gears turning beneath the surface of physics.
Exactly. And today, we have a truly monumental mission ahead of us. We are going to explore the geometric foundations of Hermann Weyl's gauge theory. This is a concept that didn't just tweak the margins of 20th century theoretical physics and differential geometry. It completely flipped them on their head. It laid the groundwork for how we currently understand the entire quantum world.
It was a total paradigm shift, and to guide us on this journey, we're using a highly detailed, line-by-line, exhaustive text that has been translated from Korean. This source material is remarkable in its rigor. It breaks down the historical philosophy, the detailed mathematical derivations, and the foundational concepts of differential geometry with microscopic precision.
Yeah, it is designed to take you from the basic conceptual building blocks of curved space all the way up to the complex tensor mathematics that define modern physics. And our mission today is very specific. We are going to progress strictly linearly through this text.
Right, moving sentence by sentence, paragraph by paragraph, formula by formula.
Leaving absolutely no stone unturned. We are operating under the assumption that we have infinite time to truly understand how the universe's fundamental forces are written in the language of geometry. We will deconstruct every concept in extreme granularity. If there's a complex formula, we won't just skip over it. We will break down exactly what it means, why it exists, and how you can visualize it in your mind's eye.
The goal here is to build your understanding from the ground up, starting with the simplest assumptions and ending with the architecture of the cosmos. You are going to see how abstract mathematical structures become the physical forces you experience every day. It is a profound, intellectually rigorous journey, and we are going to take it one careful step at a time, ensuring that the logic flows perfectly from one point to the next.
That covers the overview and mission of our deep dive. Have we missed any nuances regarding our approach today?
I think we've thoroughly unpacked it. Let's proceed to the first section on the philosophical and historical context of 1915 to 1918.
Okay, let's unpack this. The source begins by analyzing a very specific monumental sentence from history. It reads, quote, "To mathematically implement this idea, Weyl introduced a new geometric structure."
Unquote. Right.
Now, to understand the weight of this single sentence, we have to rewind the clock to a very specific moment in human history. The year is 1915. Albert Einstein has just published his general theory of relativity. Before this moment, humanity, heavily influenced by the incredible work of Isaac Newton, centuries prior viewed reality through a very specific lens.
A very rigid lens.
Newtonian gravity was seen as an invisible tether, an instantaneous force, pulling objects together across a flat, static, unchanging stage of space. If you imagine the universe as a theater, space and time were just the wooden stage and the ticking clock on the wall. They didn't do anything. Things just happened inside them. Einstein completely shattered that view.
The paradigm shift that Einstein introduced really cannot be overstated. We need to look at why this was so disruptive. He proposed that gravity isn't a pull at all. There is no invisible tether. Instead, gravity is the physical curvature of space-time itself. The theater stage is not rigid. It is a flexible, dynamic fabric.
Right.
Massive objects like the sun don't actively reach out and pull on the Earth. Instead, their sheer mass warps and bends the geometry of the space around them, much like a heavy bowling ball resting on a trampoline creates a deep depression. The Earth then simply travels along the straightest possible path it can find through that locally warped geometry. Because the space is curved, that straight path ends up looking like an orbit.
It was a staggering revelation. Space was no longer a passive backdrop. It was an active, bending, flexing participant in the physics of the universe. Geometry became physics. And this brings us to 1918, just 3 years after Einstein's earth-shattering publication. Enter Hermann Weyl.
A brilliant mathematician and physicist.
He is looking at Einstein's work, and he's profoundly inspired. He looks at this beautiful, elegant geometric explanation for gravity and begins to dream of something even bigger, something that has captivated physicists ever since. A unified field theory. We have to remember where science was at this time. Humanity only really knew of 2 fundamental forces in the universe. There was gravity, which Einstein had just brilliantly explained with the geometry of curved space, and there was electromagnetism, the force responsible for light, electricity, and magnetism, which had been codified by James Clerk Maxwell in the 1800s.
So Weyl thought to himself, if gravity is geometry, couldn't electromagnetism be geometry too? He was deeply troubled by a universe divided. Why should the cosmos have 2 entirely different mechanisms for its fundamental forces? Why should gravity get to be this beautiful intrinsic curvature of the fabric of reality, while electromagnetism is relegated to being this invisible, abstract field just living on top of that space, completely separate from the geometry?
So his ambition was to show that electromagnetism wasn't just sitting in space. It was an inherent property of the space itself. He is essentially saying that the universe speaks only one language, and that language is geometry. Everything we experience, whether it's an apple falling from a tree or a glowing light bulb illuminating a room, is just a different dialect of the exact same geometric mathematical structure. He wanted to prove that reality is a monolith.
That is precisely what he wanted to prove. But to make electromagnetism pop out of the geometry naturally, Weyl realized that Einstein's version of geometry, which was strictly based on Riemannian geometry, wasn't quite flexible enough. Einstein had bent the direction of space to create gravity, but he had left something else completely untouched. Weyl realized he had to invent an entirely new geometric structure, as our source text quotes, to fulfill his dream. He had to rewrite the fundamental rules of geometry itself to make room for light.
That covers the philosophical and historical context of 1915 to 1918. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence regarding the crucial shift from absolute to relative scale.
The source text moves on to analyze this fascinating sentence regarding Weyl's new geometry. Quote, he modified the connection so that when a vector is parallel transported, not only its direction, but also its length can change, unquote. This brings us to a massive philosophical conflict. We know Einstein's special and general relativity prove that space and time are relative to the observer. If you move incredibly fast, close to the speed of light, time actually slows down for you relative to someone standing still. The rigid, absolute framework of Newton's ticking clock was gone. However, according to the text, there was a major catch in Einstein's work, right?
Yes, a very subtle but critical catch. This raises an important question. What did Einstein still consider absolute even after he tore down the Newtonian worldview? Even in the brilliantly relative world of general relativity, Einstein treated the concept of length or scale as an absolute universal constant. To put it in relatable terms, imagine you have a standard 1-meter ruler, maybe made of titanium, sitting right here in your room. If you were to magically transport that exact ruler across the cosmos all the way to the Andromeda galaxy, taking a path that weaves through the intense gravitational fields of black holes, supernovas, and dense star clusters.
Einstein's mathematics assumed that when it finally arrived in Andromeda, it would still represent exactly, objectively, 1 meter.
Exactly. So Einstein allowed the direction the ruler was pointing to change as it surfed along the curves of space-time, but the physical magnitude of the ruler, the actual distance between the 0 mark and the 1 meter mark, was a sacred constant that geometry couldn't touch. The local curvature dictated the path, but the scale of the ruler itself remained an absolute constant throughout the entire universe.
Here is where Weyl's philosophical rebellion comes into play. Weyl looks at this assumption of an absolute 1 meter ruler and essentially calls it a philosophical half measure. He says, wait a minute, if space-time is this flexible, curved, dynamic fabric where time can dilate and space can warp, why on earth should the scale of length be the one thing that remains stubbornly absolute? He argued that true, pure relativity should mean that the very standard of what constitutes 1 meter can change depending on its position in the universe and the specific path it took to get there.
It is a profound philosophical objection. Think deeply about the thought experiment of moving a ruler or a vector, an arrow representing a physical quantity, through curved space. In Einstein's universe, if you slide that arrow along a curved path, the direction of the arrow changes. This makes intuitive sense to us. If you walk along the curved surface of the Earth, your concept of forward or horizontal changes relative to a fixed point in absolute space.
Right.
You're following the curve. But the magnitude, the physical length of the arrow, is strictly preserved by the math. Weyl argued that this preservation of length was an artificial restriction we placed on the math because of our human bias toward rigid rulers. He proposed that as you move that vector, the geometry of space itself should be allowed to actively stretch or shrink the vector.
Let me make sure I'm visualizing this correctly. We are talking about a fundamental difference between changing where an arrow points and changing how long the arrow physically is. Weyl is saying that space dictates both. Space tells things how to move by curving their direction, but it also tells things how to scale by stretching and shrinking their magnitude. This is a radical modification of the underlying geometry.
It was incredibly radical, and it upset Einstein greatly at first. Weyl essentially stated mathematically that there is no absolute size in the universe. What you perceive as a meter here on Earth might be mathematically perceived as a millimeter somewhere else in a different gravitational or geometric context. And there is no God's eye view outside the universe to say which one is the true objective meter. The scale is entirely relative to the local geometry. This concept is actually the origin of the term gauge. In historical terms, a gauge referred to a standard of measurement, like the gauge of a railroad track. Weyl was introducing a theory where the scale could change.
That covers the philosophical shift from absolute to relative scale. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence, introducing the mathematical object invented for this scale change.
Okay, the source now analyzes the following sentence. Quote, in addition to the Levi-Civita connection of Riemannian geometry, a new one-form describing the scale change was introduced. Unquote. Let's break down the specific mathematical tools being used here. As we mentioned, Einstein's tool for mapping the curvature of general relativity was Riemannian geometry, and the specific mathematical mechanism inside that geometry that handles the curving of direction is called the Levi-Civita connection.
Named after the brilliant Italian mathematician Tullio Levi-Civita. The Levi-Civita connection is essentially the mathematical instruction manual that tells you exactly how an arrow's direction twists as you slide it across a curved surface. If you are moving a vector over a sphere, the Levi-Civita connection provides the exact geometric rules for how to update the vector's coordinates so it stays as straight as possible on that curved surface. But, as we just established, it is strictly designed at a foundational level to preserve length. It has zero mathematical mechanism for stretching or shrinking the arrow.
So, to implement his radical idea that scale can change, Weyl had to introduce a brand new mathematical object to sit alongside the Levi-Civita connection. This new object needed to dictate exactly how much the length of our vector stretches or shrinks at every single infinitesimal point in spacetime. This object is what mathematicians call a one-form.
And here is the eureka moment, the part that makes shivers run down a physicist's spine. Weyl constructed this new mathematical object, this one form, solely to dictate scale change. It was a purely geometric invention to solve a geometric puzzle he created for himself. But when he stepped back and looked at the resulting equations describing this one form in four-dimensional spacetime, he realized something incredible. This geometric object took the exact mathematical shape, possessing the exact same number of components and transformation rules as the electromagnetic vector potential found in Maxwell's physics.
That is mind-blowing. Let's pause and appreciate that. By simply allowing the scale of a ruler to change in his math, electromagnetism magically popped out of the geometry equations. He didn't force physical magnets or electricity into his theory. Electromagnetism was a natural, unavoidable consequence of allowing geometry to stretch. Before we move further, let's make sure we have the exact mathematical representations of these two concepts down perfectly so you can visualize the notation. The Levi-Civita connection,
Gamma lambda mu.
gamma upper lambda lower mu nu, and the new one form,
Phi lower mu.
getting familiar with those symbols is crucial. The Levi-Civita connection, that gamma symbol with its three indices, represents the twisting of direction. The new one form, the Phi symbol with its single lower index, represents the scaling of length. Together, in Weyl's brilliant mind, they formed a complete, unified picture of the universe's forces. He believed that gravity emerged from the twisting gamma, and electromagnetism emerged from the scaling phi. It is an incredible story of mathematical beauty leading to physical revelation. Now, the history books tell us that Einstein later found physical issues with Weyl's specific theory. Einstein pointed out that if scale truly changed based on path, then two hydrogen atoms that took different paths through the universe would end up being different sizes, which means they would emit light at different frequencies. Since all hydrogen atoms we observe seem to be exactly identical regardless of their history, Weyl's literal geometric interpretation had a flaw.
That is the tragic but beautiful irony of science. Weyl was wrong about the specific geometry explaining the macroscopic electromagnetic field, but the underlying concept of gauge theory, the idea that a local symmetry or local change in scale requires a new mathematical field to compensate for it, survived. When quantum mechanics came along a decade later, physicists adopted Weyl's exact mathematical framework. Instead of changing physical length, they applied his gauge transformation to the phase of quantum wave functions. And it worked perfectly. Weyl's invention became the absolute foundation for the entire modern standard model of particle physics.
That covers the introduction of the one form and the Levi-Civita connection. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to section 1 of the source, detailing the foundational spaces where this math actually happens.
We are now officially moving to section 1 of the source text, which lays the absolute geometric foundations. Before we can do the advanced math of gauge theory or general relativity, we need to rigorously define the mathematical space where this math is taking place. Most of us are very comfortable with what is called Euclidean space. This is the flat Cartesian coordinate system we all learn in middle school geometry. You have an x-axis going left and right, a y-axis going up and down, and a z-axis giving you depth. They are perfectly straight lines, they meet at exact 90-degree angles, and they go on forever in perfectly rigid grid lines.
In that Euclidean space, working with vectors is very simple. A vector is just an arrow with a length and a direction. The beautiful, comforting thing about Euclidean space is that it is globally flat. This means you can take an arrow drawn at coordinates 1, 1, pick it up and slide it to coordinates 100, 100, and it fundamentally remains the exact same arrow. Its length and its angle relative to the underlying grid never change. You don't have to do any special math to move it or compare it. Space is just a passive empty box.
But the universe, as Einstein proved, isn't a flat grid. It is what mathematicians call a manifold. The source text defines a manifold as a mathematical space that is globally curved but locally flat. Let's use a mental image to make this clear. Think about the surface of the Earth. If you look at the Earth from the International Space Station, it is clearly a curved three-dimensional sphere. But if you walk out into a large grassy football field, the ground beneath your feet looks and feels perfectly flat. You can draw a straight XY coordinate grid on that field, and for all practical purposes, the Pythagorean theorem and basic flat math work perfectly.
That is the very essence of a manifold. You can stitch together an infinite number of these microscopic, locally flat patches to describe a massive, globally curved object. However, while this solves the problem of how to describe curves, it introduces a massive mathematical headache when it comes to dealing with vectors. Remember, a vector is geometrically defined as a perfectly straight, rigid arrow. You cannot draw a perfectly straight, rigid arrow flush against a globally curved surface. If you try to lay a straight stick on a basketball, only one tiny point of the stick touches the ball. The rest sticks out into the air.
Here's where it gets really interesting. If the arrows can't bend, where do the vectors actually live in this math? The text explains they live in what is called a tangent space. If you picture this in your head, imagine that basketball again. Now imagine taking a perfectly flat, rigid piece of cardboard and balancing it delicately on the very top of the basketball, so it only touches at exactly one single microscopic point. That flat piece of cardboard represents the tangent space at that specific point. Let's call that point P. We denote this space mathematically as the tangent space of point P on manifold M.
And any vector, any straight arrow that you want to define at that specific point P must live exclusively on that flat piece of cardboard. It cannot exist on the curved surface itself. Now imagine picking another point Q on the side of the basketball. You balance a second flat piece of cardboard there. That is the tangent space at point Q. Because it's on the side of the ball, it is a completely different flat plane, tilted at a completely different angle in the broader 3D space compared to the first piece of cardboard.
So here is the colossal problem the source text points out, and it's a hurdle every student of differential geometry has to overcome. A vector at point P lives in a totally differently angled flat plane than a vector at point Q. In flat Euclidean space, if I want to add two vectors together or compare them, I just slide one over to the other and put them tail to tip. But how on earth do you compare, add, or subtract a vector sitting on the top cardboard plane with a vector sitting on the side cardboard plane?
You can't just slide them directly through the air. And if you try to slide a vector off its tangent plane and force it onto the curved surface to move it, it loses its mathematical definition as a straight vector. Let's use an extreme example to show why direct comparison fails. Imagine trying to compare an arrow pointing directly north at the equator with an arrow pointing north at the North Pole. At the equator, your tangent space, the ground, is standing up vertically relative to the Earth's axis, and the vector pointing north is parallel to the ground, pointing up toward the top of the globe. But at the North Pole, your tangent space is horizontal, and every single direction on that plane is south. The very concept of north fundamentally changes depending on which tangent space you are in. You are comparing apples to oranges.
This means we need a rigorous mathematical machine. We need an algorithm to translate a vector from one flat tangent space to another flat tangent space, slowly walking it across the curved manifold, without losing the physical essence of what that vector represents. That covers the foundational concepts of manifolds and tangent spaces. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next section, detailing parallel transport and the covariant derivative.
To solve the immense problem of comparing vectors in entirely different tangent spaces, the source text introduces the concept of parallel transport. This is the mathematical machine we just alluded to. The primary goal of parallel transport is to carefully move a vector along a specific path from point P to point Q while maintaining its core properties, its direction and its length, as faithfully as mathematically possible within the strict constraints of the underlying curved space.
This brings us to a crucial distinction in how we calculate change in calculus. In our familiar, comforting, flat Euclidean space, if we want to know how a vector field changes as we move along a coordinate axis, we use a tool called a simple partial derivative. For those who might be rusty, a partial derivative simply measures the raw rate of change in the numerical components of the vector as you nudge it slightly in one direction. It's like looking at a speedometer. It just gives you the raw change in numbers.
Hold on, let me stop you there because I want to make sure the failure of this tool is clear. The source explicitly states that in a curved space manifold, relying on the simple partial derivative completely fails. It gives you garbage data. Why?
We need to understand why it fails. Because on a curved manifold, the coordinate axes themselves, the grid lines you are using to measure, are actively bending, twisting, and expanding along the surface. If you look at your math and see the numbers describing your vector change, you are faced with an ambiguity. You don't know if the vector itself actually changed physically, or if the vector stayed perfectly still and the underlying grid you are using to measure it simply twisted beneath it.
It's like trying to measure the speed of a person walking on a moving train. If you are standing on the ground outside and you use your radar gun, your partial derivative, you measure the person moving at 60 miles per hour. That's the raw change in coordinates. But that is largely an illusion caused by the train. To find the real physical change, how fast the person is actually walking relative to the floor, you have to subtract the speed of the train itself.
That is a perfect intuitive analogy. In geometry, this raises an important question. How do we mathematically extract the real physical change of the vector from the messy, illusion-filled coordinate data? The source provides a brilliant conceptual formula to solve this. The real physical change equals the total apparent change in the coordinates minus the fake change caused by the bending of the coordinate axes themselves.
And this resulting mathematically pure, real physical change is what mathematicians call the covariant derivative. This is the holy grail of differential geometry. Let's look at the exact mathematical formulation of this critical concept as provided in the text, the covariant derivative equation.
Nablano v mu plus gamma mu nu plus gamma mu mu equals the partial derivative lower nu of v upper mu plus gamma upper mu lower nu lambda times v upper lambda. Let's deeply deconstruct the y behind every single term in this equation, as it is the beating heart of all differential geometry. On the far left side, we have the nabla symbol operating on v. This is the covariant derivative. This represents the pure, objective physical reality. It is the real intrinsic change of the vector as it moves through the space, completely independent of whatever crazy, twisty coordinate system you happen to be using.
Moving to the right side of the equal sign, the first term uses the partial derivative symbol, which looks like a curly D. This represents the total apparent change in the coordinates. It's the radar gun reading from outside the train, is what your raw, uncorrected mathematical data shows.
And finally, the second term on the right side is our crucial correction factor. We see our old friend from earlier, the gamma symbol, the connection coefficient, which is also called the Christoffel symbol. In this term, it is multiplied by the vector v itself. This entire term represents the fake change, the speed of the train. The gamma symbol is essentially the architectural blueprint of the curved space. It is a mathematical object that encodes exactly how much the coordinate grid twists, turns, and scales as you move from one infinitesimal point to the next. By adding this geometric correction factor to our raw data, we perfectly strip away the illusion caused by the curved grid, leaving only the pure covariant derivative on the left, the absolute truth of the vector's motion.
The covariant derivative is the ultimate tool that allows the laws of physics to remain objective in a universe where the measuring grid is constantly warping due to gravity. It is how Einstein ensures the laws of physics are the same everywhere. That covers parallel transport and the covariant derivative equation. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next section on the metric tensor.
We are now moving to section 2 of the source text. Now that we've established how to move and compare vectors using the covariant derivative, we need a way to actually measure fundamental distances and angles on our curved manifold. We need the mathematical equivalent of a physical ruler. In differential geometry, the concept of the ruler is embodied by a mathematical object called the metric tensor.
To truly grasp the metric tensor, we need to contrast it with our familiar flat space one more time. In flat Euclidean space, distance is calculated using the ancient Pythagorean theorem, a squared plus b squared equals c squared. If you want to represent the simple rule mathematically as a matrix grid of numbers, it is incredibly boring. It is represented by what's called an identity matrix. An identity matrix is just a diagonal line of the number 1 with zeros everywhere else in the grid. It tells you that moving one unit in the x direction always equals a distance of 1 anywhere, forever. It's constant, rigid, and never changes.
But in curved space, the rules of distance change dynamically from point to point. Think about looking at a flat 2D map of the Earth, like the Mercator projection. A straight line path drawn on that flat paper from New York to London is not actually the shortest physical distance when you wrap that map around a globe. The flat map distorts distance. The metric tensor is a complex matrix filled not with boring ones and zeros, but with complex mathematical functions that define exactly how distance is calculated at every specific microscopic coordinate location. It dynamically adapts to the curvature. It tells you how much a coordinate step counts toward actual physical distance at that exact spot. Let's look at how the source text mathematically defines the measurement of a tiny infinitesimal distance using this metric tensor. The infinitesimal distance squared.
ds squared equals g lower mu nu times dx upper mu times dx upper nu. This elegant little equation is the absolute foundation of all metric geometry. Let's break it down. On the left, we have d squared, which is the infinitesimal distance squared. It represents the absolute tiniest imaginable physical step you can take in the space. On the right, we have the metric tensor, denoted by the letter g, interacting with dx, which represents the infinitesimal changes in your coordinate grid directions.
Okay, let me stop you there because we need to unpack the notation on the right side of the equation. The source text explicitly points out a brilliant mathematical shortcut used here, invented by Einstein himself, called the Einstein summation convention. If you picture this equation in your head, imagine the Greek letters mu and nu. On the metric tensor g, they are sitting down at the bottom as subscripts. But on the dx terms, they're floating up top as superscripts.
Yes, this notation is crucial to understand because it hides massive complexity. Albert Einstein was doing so much of this grueling tensor math by hand that he got incredibly tired of writing the big Greek sigma summation symbol over and over again. So he instituted a rule for physicists. Whenever you see an index, like mu or nu, repeated exactly once as an upper index and exactly once as a lower index within a single mathematical term, you automatically assume that you must sum that term over all available dimensions of your space. The summation symbol is implied.
Right. So to put that in perspective, if we are analyzing a four-dimensional spacetime with coordinates representing time, x, y, and z, which mathematicians number as dimensions 0, 1, 2, and 3, the seemingly tiny expression on the right is actually a highly compressed way of writing a massive, sprawling mathematical sum of 16 different terms. You have to plug in 0 for mu and O for nu, calculate that. You plug in 0 for mu and 1 for nu, calculate that. You do this for all 16 combinations of the four dimensions, adding them all up to get the single physical distance d squared.
It is an incredibly elegant notation that cleans up the equations beautifully on the chalkboard. But the physical meaning is what matters most. The metric tensor G is a collection of 16 independent mathematical functions spread across spacetime. It tells you everything you could possibly need to know about the shape, curves, and scale of the universe at a specific point. It is the ultimate ruler. If you know the exact values of the metric tensor everywhere, you know the entire geometry of the universe.
That covers the metric tensor and the infinitesimal distance squared equation. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next section on the two grand principles of Riemannian geometry.
The source text now lays out what it calls the two grand principles of Riemannian geometry. These are the absolute, non-negotiable bedrock rules that mathematicians established and that Einstein relied upon completely to build his theory of general relativity. These principles act as constraints. They tame the chaos of curved space and force the math to actually work predictably.
Without these two rigid principles, the mathematics of differential geometry would be too loose, too ambiguous. You could theoretically have an infinite number of different connection gamma symbols that could roughly describe the same space. These principles ensure that there is only one unique, perfectly logical way to define how space curves given a specific metric tensor ruler.
Let's delve into Principle 1, metric compatibility. The text states that when you are moving through space, carefully parallel transporting a vector from point A to point B, the length which mathematicians calculate using the inner product and the relative angle of those vectors absolutely do not change.
Think carefully about what this means physically. If you take two straight vectors that are perfectly perpendicular to each other, like an L shape, and you carefully slide them along a bumpy, curved surface using the rules of parallel transport, metric compatibility demands that when you finish moving them, they are still exactly perpendicular. The curve didn't skew their angle. Furthermore, if one vector was exactly 2 meters long when you started moving it, it must be exactly 2 meters long when you reach your destination. The ruler, the metric tensor itself, never dynamically stretches or distorts as you move it through the geometry.
So the physical space around the ruler might be heavily curved by a black hole, but the ruler's fundamental definition of what constitutes a meter remains sacrosanct and untouchable. This is exactly what we discussed earlier, the assumption that Weyl will eventually rebel against. But in standard Riemannian geometry, this preservation of length is an unbreakable law. Let's look at the incredibly concise math for Principle 1, the metric compatibility condition.
Nabla lower lambda of g lower mu nu equals 0. This equation is beautiful in its absolute simplicity. It literally says that the covariant derivative, which we learned is the real physical change of the metric tensor g, is exactly 0 in all possible directions represented by lambda. The ruler does not physically change, ever.
Now let's look at Principle 2, the torsion-free condition. The text says that the connection coefficients, our gamma symbols, must be symmetric. What this means geometrically is that if you trace out a parallelogram shape, say, you move vector A along the path of vector B, and then you move vector B along the path of vector A, you will yield a perfectly closed loop where the endpoints meet exactly, with no gaps or weird twists.
To visualize the alternative, if the space had torsion, you wouldn't end up where you started. Imagine trying to draw a flat square on a surface that is not only curved, but actively twisting like a spiral staircase. You go forward, turn 90 degrees, go forward, turn 90 degrees.
And instead of closing the square, you end up hovering slightly above your starting point on the next step of the staircase.
Exactly. That physical gap between your start and end point is called torsion. Einstein's theory of gravity assumes space-time has curvature, like hills and valleys, but absolutely zero torsion. It is perfectly smooth at a local level. Let's read the mathematical condition that enforces this smoothness. the torsion-free condition. Gamma lambda gamma lower nu equals gamma upper lambda lower nu.
If you picture the equation, notice how the two lower indices, mu and nu, are simply swapped on the right side. This mathematical symmetry guarantees that the order in which you traverse the coordinate directions doesn't matter. It doesn't introduce any twisted gaps. These two principles combined, metric compatibility and the torsion-free condition, form the rigid, inescapable scaffolding upon which the rest of the mathematics of relativity is built.
That covers the two grand principles of Riemannian geometry. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the mathematical derivations steps 1 and 2. Now we reach a truly spectacular, incredibly dense part of the source text. It walks us through a painstaking, step-by-step mathematical derivation of the Levi-Civita connection. The overarching goal here is profound. We want to derive the blueprint of the curvature, the gamma connection symbol, using only the data from the metric tensor G. We want to mathematically prove that if you know how the ruler behaves at every point, you can calculate exactly how the entire space curves without needing any outside information.
This section is a masterclass in tensor calculus. It shows how logical constraints can force a specific mathematical reality into existence. We are going to build the architecture of curvature out of pure distance measurements. It's like reverse engineering the shape of a landscape using only a tape measure.
Step 1 of the derivation is to take the first principle we just learned, metric compatibility, where the covariant derivative of the metric is 0, and expand it using the long-form definition of the covariant derivative from earlier. Remember, the rule is that the total change is 0. But because the metric tensor G has two lower indices, mu and nu, the mathematical expansion requires two separate connection gamma terms to properly correct for the twisting in both slots of the tensor. Let's look at the expanded equation, the expanded metric compatibility equation.
Nabla I lower lambda of G lower mu nu equals the partial derivative lower lambda of G lower mu nu minus gamma upper rho. Lower lambda mu times G lower rho nu minus gamma upper rho lower lambda nu times G lower mu rho equals 0.
This looks incredibly complex, a soup of Greek letters, but conceptually it's just a direct translation of our rules. It says the real physical change of the metric, which we know is strictly 0, equals the raw apparent coordinate change of the metric, minus the geometric corrections for how the grid twists along the mu direction, minus the corrections for how the grid twists along the nu direction. Because the whole thing equals 0, we can use basic algebra to move terms across the equal sign and isolate the apparent coordinate change on one side.
Let's look at that rearranged equation, which the text labels as equation A, the rearranged equation A.
And plus gamma partial derivative lower lambda of G lower mu nu equals gamma upper rho lower lambda mu times G lower rho nu plus gamma upper rho lower lambda nu times G lower mu nu. Equation A gives us a crucial insight. It tells us that any apparent change in our ruler's measurements as we move through our coordinate grid, which is the left side, is entirely 100% due to the curvature of space interacting with the metric itself, the right side. But our goal is to solve for the connection, the gamma terms. Right now, they are hopelessly tangled up, multiplied by the metric on the right side.
This brings us to step 2, which the source text calls the index permutation trick. It is a brilliant piece of mathematical sleight of hand. We currently have one equation with 3 free indices that can be anything, lambda, mu, and nu. We want to isolate the gamma connection, so we're going to create a larger system of linear equations. It's just like what you would do in basic high school algebra if you had multiple variables like x, y, and z. You need multiple equations to solve for them. We do this by taking equation A and writing it out 2 more times, but each time we systematically cycle the letters. Lambda becomes mu, mu becomes nu, and nu becomes lambda.
It's a beautifully simple, almost mechanical process. By cycling the indices, we generate 3 distinct equations. These 3 equations are essentially describing the exact same underlying geometry, but from 3 slightly permuted, rotating mathematical perspectives. We are setting the stage to combine these perspectives in the next step to strategically eliminate the terms we don't want, leaving only the pure connection symbol.
That covers steps 1 and 2 of deriving the Levi-Civita connection. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to steps 3 and 4 to execute the combination and complete the derivation.
Here's where the mathematical magic trick comes to its dramatic climax. In step 3, we take those 3 permuted equations we just generated and we combine them. Specifically, the source text tells us to take equation 1, add equation 2 to it, and then subtract equation 3 from the total.
When you write all of this out on a chalkboard, you end up with a massive equation. You have 3 partial derivative terms on the left side and a sprawling string of subtle different gamma connection terms on the right side. It looks like an unsolvable mess of Greek letters. But this is where the 2 grand principles we established earlier swoop in to save the day.
Exactly. Let's stop and look at the right side. Because of principle 2, the torsion-free condition, we know the connection coefficients are perfectly symmetric. So a gamma with indices lambda mu nu is mathematically identical to a gamma with indices lambda nu mu. And we also know the metric tensor G is symmetric. Because of these hidden symmetries, a massive cascade of mathematical cancellation occurs when we do that subtraction. Terms that look different at first glance are actually clones of each other, and because we are subtracting equation 3, they perfectly annihilate each other.
It is incredibly satisfying to execute on paper. 6 complex tangled terms on the right side gracefully collapse, cancel out, and reduce down to just one single neatly packaged term. Let's look at the remarkably clean equation that is left after the dust settles.
The isolated connection terms.
Partial lambda, partial nu, plus lambda, partial nu do.
The partial derivative lower lambda of g lower mu nu plus the partial derivative lower mu of g lower nu lambda minus the partial derivative lower nu of g lower lambda mu equals 2 times gamma upper O lower lambda mo times g lower rho nu.
Look at how clean that is. The left side is purely made of the partial derivatives of the metric tensor, which is raw data we can easily calculate if we know the shape of our ruler. The right side is almost exactly what we want. The gamma connection symbol multiplied by a factor of 2 and a trailing metric tensor term.
To finish the job in step 4, we need to strip away that trailing metric tensor g from the right side, so gamma is completely alone. To do this, we multiply both sides the entire equation by the inverse metric tensor.
Let's unpack what multiplying by an inverse actually does in tensor math, because it's vital. Think of a 3D video game engine. In a game engine, you have matrices that rotate or scale your character. If you apply an identity matrix, it means do nothing. The character stays exactly the same. The Kronecker delta is the tensor mathematics version of that identity matrix. It's the mathematical equivalent of an undo button. When you multiply a tensor by its exact inverse, they perfectly contract into the Kronecker delta. The metric and its inverse annihilate each other, leaving behind this identity operator, which simply shifts the index up and isolates the gamma connection symbol entirely by itself on the left side.
Let's read the final, glorious result of this derivation. This is the master equation of general relativity. The final Levi-Civita connection formula.
Gamma lambda left 11.
Gamma upper lambda lower mu nu equals 1/2 times g upper lambda rho times the quantity. The partial derivative lower mu of g lower nu rho plus the partial derivative lower nu of g lower mu rho minus the partial derivative lower rho of g lower mu nu.
If we step back and connect this massive mathematical derivation to the broader physical picture, the philosophical meaning of this final formula is profound. It proves mathematically that the curvature of space, represented by the solitary gamma symbol on the left, is 100% determined by how the ruler changes, represented by the derivatives of the geometric terms on the right. You don't need any outside information, no external absolute space. The metric dictates the geometry. This specific formula is the beating mathematical heart of Einstein's general relativity.
That covers steps 3 and 4 of the Levi-Civita derivation. We missed any nuances.
I think we've thoroughly unpacked it. Let's proceed to the next section and apply this massive formula to an example problem.
Abstract tensor algebra is incredibly powerful, but the source text wisely decides to ground this massive formula we just derived by applying it to a simple familiar space that we can easily visualize. 2D polar coordinates. So instead of navigating a city block using an X and Y grid, we are navigating using a radius r, which is how far you are from the center, and an angle theta, which is what direction you are currently facing. Think of a radar screen.
What is conceptually fascinating here is that a 2D polar plane is perfectly physically flat. If you draw a large triangle on it, the angles will add up to exactly 180 degrees. It has no intrinsic physical curvature like the surface of a sphere does. However, the coordinate grid we have chosen to use, the concentric circles of the radius and the sweeping radial lines of the angle, is highly curved. Therefore, even though the physical space is flat, the mathematical connection coefficients, the gamma symbols, will not be zero. They have to exist to tell straight vectors how to constantly twist and adjust their coordinate numbers simply to follow the artificially curved grid lines.
Let's start by defining our ruler in this polar space. The metric equation tells us exactly how to calculate a tiny physical distance given small changes in our coordinates. The polar coordinate metric.
ds2 equals dr2 plus r2 d theta.
ds squared equals dr squared plus r squared times d theta squared.
Let's translate that math into physical movement. This equation means if you step slightly outward from the center, your distance squared is just your change in radius squared. That's simple. But if you step slightly around the circle, along the curve, your distance squared is your change in angle squared, multiplied by how far out you are, the radius squared. The further from the center you are, the longer a 1-degree step physically is. This simple equation gives us the specific values to plug into our metric tensor matrix.
The text then painstakingly walks through the process of finding one specific connection coefficient using the massive Levi-Civita formula we derived earlier. We want to know exactly how the radius component of a vector forcefully changes when we move the vector purely along the sweeping angle direction. Let's look at the target symbol for this calculation. The target connection coefficient.
Gamma theta theta.
Gamma upper R lower theta theta. By meticulously plugging the values of our simple polar metric into the giant Levi-Civita formula, a wonderful thing happens. Because the metric is so simple, most of the complex partial derivative terms instantly become zero. After churning through the remaining algebra, all the complexity collapses and a single elegant mathematical term survives the derivation.
Calculated result.
Gamma R.
Gamma up par lower theta theta equals negative r. So what does this all mean? We just did a bunch of abstract math and got the answer negative r. Why is that important? How does that help us understand reality?
It is incredibly important because mathematical abstractions are most powerful when we can verify them against our physical, visceral intuition. Let's translate this mathematical result into a physical sentence. When you force an object to move along a circular angle theta, its straight line vector naturally wants to turn inward in the negative radial direction by an amount strictly proportional to its radius. Think about being a kid on a spinning playground merry-go-round. You are moving along the angle theta. What do you physically feel? You feel a phantom force trying to fling you off the edge, but to stay on the circular path, you must continuously use your arms to pull yourself inward toward the center pole. This mathematical result we just derived, negative r, is the pure geometric equivalent of that centripetal force. It mathematically proves that in order to follow a curved coordinate line, a straight vector must constantly accelerate inward. It shows that the highly abstract tensor math works flawlessly. The geometry perfectly captures the physical reality of moving in a circle. That covers the 2D polar coordinate example problem. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next section, introducing Weyl's gauge transformation.
We are now entering section 3 of the source text, and this is where the historical and scientific revolution truly happens. We spent all this time painstakingly establishing the two grand principles of Riemannian geometry, and we learned that the absolute most sacred of them was principle 1, metric compatibility. The covariant derivative of the metric is 0. The ruler never, ever changes length.
And here is where Hermann Weyl walks into the mathematical room, looks at the foundational architecture of general relativity, and deliberately breaks the first rule. He says, if we want to understand the whole universe, the ruler must be allowed to change.
To accomplish this mathematically without destroying the logical consistency of the equations, Weyl introduces what he called eigenvariance, a German term which translates to scale invariance, but which is now universally known in modern physics as a gauge transformation. He takes the sacred metric tensor, our ruler, and mathematically multiplies it by an arbitrary fluctuating scale factor. Let's look exactly at what this scale factor looks like, the scale factor.
Square to the power of
Sigma of x.
The choice of this specific mathematical exponential function is incredibly deliberate and clever. Why use the exponential function e? Because the physical length of a ruler in reality must always be a positive number. You cannot physically have a titanium ruler with a length of -2 meters. It doesn't make sense. By using the exponential function e, the math perfectly guarantees that no matter what crazy value the variable sigma takes, whether it's positive, fiercely negative, or 0, the resulting scale factor will always be a strictly positive number. It prevents the fragile geometry from instantly collapsing into non-physical absurdities.
And when we actually apply this scaling factor to the metric tensor g in the equations, we have to square it. Why the 2? Because as we saw earlier, the metric tensor doesn't measure pure linear distance. It measures distance squared, as in the ds squared equation. Let's look at the full mathematical transformation, the gauge transformation of the metric.
G lower mu of x maps to g sol lower mu of x, which equals e to the power of 2 sigma of x times g lower mu of x. This relatively short equation represents a profound shift in human perspective regarding reality. It mathematically states that the true metric, the completely new reality denoted by the metric with the tilde over it, is just the old, rigid Einstein metric multiplied by this wild, local scaling factor. The scale of the universe can now violently fluctuate based entirely on your location x.
But breaking the fundamental rules of geometry has massive mathematical consequences. Because the scale can now change arbitrarily based on location, the standard Levi-Civita connection we spent so long deriving is no longer mathematically sufficient. It only knows how to twist. It doesn't know how to handle stretching. To fix the equations he just broke, Weyl absolutely needed a new mathematical field to act as an instruction manual, tracking exactly how the scale changes as you move through all 4 dimensions of spacetime: x, y, z, and time.
This brings the historical narrative full circle. Because Einstein's spacetime is 4-dimensional, this new instruction manual for scaling needs 4 distinct, independent components to tell a vector exactly how to stretch or shrink if it moves in any of those 4 specific directions. This absolute, unavoidable mathematical necessity for a 4-component geometric scaling field is exactly what gave birth to the one-form. The one-form was the mathematical structure that serendipitously, miraculously mirrored the 4-component vector potential of electromagnetism.
That covers Weyl's gauge transformation and scale invariance. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the final section defining the one-form mathematically.
We are at the final section of the source text, where it rigorously defines the fundamental nature of the one-form we just introduced. To truly grasp what a one-form is in differential geometry, the text contrasts it heavily with a standard vector.
We are very familiar by now with standard vectors, which mathematicians technically call contravariant vectors. Let's look at the specific notation so we can visually separate them. The contravariant vector.
V upper mu.
Picture this in your head. Notice the upper index. In the visual geometric language of physics, a contravariant vector with an upper index is an arrow. It has a specific physical magnitude and a specific direction. It actively represents physical movement, velocity, or a forceful push through space. It is an active, moving participant in the geometry.
Now contrast this with a one-form, which is mathematically called a covariant vector or covector. The covariant vector, or one-form. Philomer.
Picture this. Notice the lower index. This is a fundamentally different type of mathematical beast. The source text emphasizes very strongly that you should not visualize a one-form as an arrow. That will lead you mathematically astray. Instead, you should visualize a one-form as a topographic map, a series of infinite stacked contour lines spread widely across the space.
Think about looking at a hiking map of a steep mountain. The contour lines drawn on the map don't point anywhere. They don't have a direction like an arrow. They just sit there passively, representing the elevation gradient. A one-form mathematically acts as a linear function. Its entire purpose in life, its geometric destiny, is to wait passively for a standard vector, an active arrow, to be mathematically plugged into it. When you push an arrow through a one-form, the math calculates exactly how many of those contour lines the arrow physically pierces through, and it outputs a single clean scalar number.
If we connect this to the bigger picture, the beauty of this distinction is staggering. Remember, Weyl needed a field to tell the geometry exactly how many units of scaling a vector experiences as it moves from point A to point B. The one-form, this series of contour lines, is the absolute perfect mathematical tool for the job. You plug your physical movement vector into the geometric scaling one-form, and it spits out exactly how much your ruler needs to stretch or shrink along that specific path.
And mathematically, this one-form, this passive set of contour lines with its lower index, behaves absolutely perfectly under complex coordinate transformations to represent a fundamental force field in reality. This specific one-form, this series of contour lines dictating how the geometry of the universe stretches, was the exact identical mathematical puzzle piece needed to flawlessly describe the electromagnetic field.
Reflect on the sheer, breathtaking beauty of that historical moment. Weyl didn't perform a physical experiment with magnets and copper wire to find this equation. He was sitting at a desk, looking at the abstract, rigid rules of differential geometry, and decided on a philosophical whim to change one basic assumption about how we measure the physical length of a line. By altering that abstract mathematical rule, he inadvertently built a mathematically rigorous bridge directly to the physical reality of electromagnetism. It remains one of the most elegant, unexpected conceptual leaps in the entire history of science.
That covers the definition of the one-form mathematically. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to wrap up this entire discussion.
We've covered an incredible, massive amount of ground today. We started with a simple historical sentence about a new geometric structure proposed in 1918, and we painstakingly unpacked it all the way down to the foundational math of tensors, manifolds, covariant derivatives, and gauge transformations. But let's bring this back to you, the listener. Why should you care about this intense, exhaustive dive into esoteric mathematics? Because understanding this fundamentally shifts how you should view the reality you live in every day. It proves that the universe isn't just a flat, boring stage where independent forces just happen to bump into each other. The shape, the scaling rules, and the fundamental geometry are the forces themselves. Everything is intimately mathematically connected at the deepest possible level.
By daring to question an assumed absolute, like the incredibly common sense idea that the physical length of a titanium ruler never magically changes, Weyl unlocked an entirely new, revolutionary way to describe the fabric of reality. It is the ultimate testament to the immense power of critical thinking and mathematical exploration. We must constantly, relentlessly examine our bedrock assumptions, because the next great leap in human understanding is often hiding just behind the rule we were told never to break.
And I want to leave you with a final, provocative thought to mull over, something that pushes beyond the text we read today. We saw how allowing the continuous scale of space to locally fluctuate gave us the mathematics of electromagnetism out of thin air. What other fundamental forces might pop out of the equations if we rethink other deeply held geometric assumptions? What if, for example, we assume space isn't perfectly, infinitely continuous at all? What if space is actually pixelated or discrete at the extreme quantum level, like a digital photograph? What brand new, universe-altering physics is hiding in the math right now, just waiting for someone brave enough to break the rules of geometry all over again?
It's a thrilling, terrifying question, and it's exactly the kind radical mathematical thinking that will undoubtedly drive the next great revolution in theoretical physics.
Thank you for joining us on this exhaustive deep dive. Keep questioning the structure of your reality.
Imagine for a second that you are holding a standard 1-meter wooden ruler. You walk across your living room, you measure the coffee table, and it's 1 meter long. Now imagine you take that exact same ruler, walk out your front door, down the street, and into a slightly different gravitational field. You hold up the ruler again, but now
It's only 1/2 meter long.
right. The physical wood has shrunk just because of the path you took through space. Welcome, everyone. We are thrilled to have you with us for this deep dive. Today, we are undertaking a truly exhaustive mission. We are looking at the mathematics of a universe where that shrinking ruler is exactly what happens. We're diving into the brilliant, slightly heretical mind of Hermann Weyl and his 1918 attempt to rewrite the absolute fundamental rules of geometry to unify the entire universe.
It really is one of the most fascinating failed theories in the history of physics. Though, to be fair, failed is entirely the wrong word. What Weyl did was fundamentally question a hidden assumption in Albert Einstein's brand new theory of gravity. And in doing so, even though his physical model wasn't quite right for the macroscopic world, he accidentally birthed the mathematical framework gauge theory that underpins almost all of modern quantum physics.
It's an incredible story of pure mathematical aesthetics driving physical discovery. And to do it justice, we are going to employ a very specific analytical approach today. We call it the unabridged protocol. Because of the sheer density of our source material, which is a masterclass text on Weyl and the geometric foundations of gauge theory, we are going to process this text strictly in linear order.
Right, line by line.
Exactly. Paragraph by paragraph, formula by formula. We are leaving absolutely no stone unturned. We aren't just summarizing. We're going to deconstruct the logical connection of every single concept.
And that is so necessary, because understanding this text is the key to seeing how humanity learned to translate the physical forces of the universe, the pushes and pulls you feel every day, into pure geometry. You can't just skip to the final equations.
Yeah.
You have to understand the geometric architecture that Einstein had just finalized a few years prior in 1915 with general relativity.
Okay, let's jump right into the text. Body section 1, looking at the philosophical and historical anatomy of the opening quote. The source text begins with this sentence. To implement this idea mathematically, Weyl introduced a new geometric structure. Let's stop right there. What is this idea? We need the 1918 historical context.
Well, the world is in chaos with World War I, but theoretical physics has just experienced its biggest revolution since Isaac Newton. In 1915, Einstein publishes general relativity. He shatters the Newtonian paradigm where space was just an empty, flat, passive container. Einstein says, no, space and time are inextricably linked into a four-dimensional fabric, right? And this fabric bends. Massive objects warp the geometric fabric around them, so gravity literally is geometry, but that left a massive philosophical problem for physicists. At the time, humanity only really knew about two fundamental forces: gravity, which is now beautiful geometry, and electromagnetism.
Light, magnetism, electricity. And to someone like Weyl, having two entirely different operating systems for the universe was, it was just ugly.
Yeah, exactly. He wanted the unified field theory. He reasoned that if gravity is geometry, why not electromagnetism? That is this idea the text is referring to.
That covers the first historical sentence. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
The text continues. He modified the connection so that when parallel transporting a vector, not only its direction but also its length could change. Let's dig into this shift from the absolute to the relative.
This is the core of his heresy. Einstein made time relative, he made space relative, but length, the scale of the universe, was still absolute. In Einstein's universe, a 1-meter ruler here on Earth is assumed to be exactly 1 meter in the Andromeda galaxy, no matter how it got there.
But Weyl looked at that and basically asked, if the very fabric of space-time is curved and twisting, why is the scale absolute? Why do we assume a meter never changes? He wanted to make scale relative to your path.
Which means, bringing it back to you, the listener, if you walk around a warped space-time manifold, your ruler is dynamically stretching and shrinking.
That covers the second sentence. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
The text states, in addition to the Levi-Civitic connection of Riemannian geometry, he introduced a new one form describing scale changes. Okay, we are hitting our first mathematical skeleton here. Let's break this down. The text mentions the Levi-Civitic connection, gamma lambda mu, the Levi-Civitic connection, capital gamma with upper index lambda and lower indices mu and nu.
Right, and we will derive that exact object later. But for now, you just need to know that capital gamma only handles direction. It tells the vector how to twist. But to handle length changes, Weyl had to invent a completely new mathematical object,
which the text calls the new one form, phi mu, the one form phi with lower index mu.
Yes, and the absolute breakthrough, the aha moment of this entire historical period is that when Weyl analyzed this new geometric object that just changed the scale of a ruler, it turned out to be the exact mathematical equivalent of the electromagnetic vector potential. Mu, the electromagnetic vector potential A with lower index mu. He generated electromagnetism purely from geometry.
That covers the third sentence. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to chapter 1.
Moving to chapter 1, establishing fundamental concepts. The text explicitly contrasts flat space with curved space. We need to define a manifold.
This is a crucial digression because this is the sandbox they're playing in. High school geometry happens in Euclidean space, a flat Cartesian coordinate plane.
Where you can just slide vectors around anywhere, right?
Exactly. An arrow in the top corner is the same as an arrow in the bottom corner. But a manifold is completely different. A manifold is a space that is locally flat, but globally curved. Think of the surface of the Earth. If you go outside, the street looks perfectly flat. You can use high school math to build a house.
But if you walk 10,000 miles in a straight line, you realize you're on a sphere.
Precisely. And that intrinsic curvature creates a massive problem for vectors. A vector is a perfectly straight arrow. You cannot lay a straight arrow perfectly flat against the curved surface of a globe. It physically doesn't fit.
So the mathematicians had to invent something called a tangent space. TPM, the tangent space T sub P of the manifold script M.
Yes. Imagine taking a perfectly flat, rigid pane of glass and resting it on a basketball so it touches at exactly one point.
Okay.
Let's call that point P. That pane of glass is the tangent space. All the vectors that exist at point P actually live on that flat pane of glass, not on the basketball itself.
But if I have another vector at point Q on the other side of the basketball...
It has its own pane of glass. And because the basketball is curved, those two panes of glass are tilted at completely different angles. They intersect. There are different realities. You cannot simply slide a vector from point P to point Q to add or subtract them. Standard calculus completely breaks down.
That covers manifolds and tangent spaces. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to parallel transport.
The text introduces the solution to this problem: parallel transport and the covariant derivative. If we can't slide arrows, how do we move them?
You have to carefully slide the vector along the curved surface, adjusting its angle continuously so it remains as constant as possible relative to the twisting space beneath it. It's like driving on a twisting mountain road while trying to keep a compass needle pointing perfectly straight relative to the dashboard. You have to actively fight the turning of the car.
To do this mathematically, the text gives us the covariant derivative equation. Nabla nu v mu plus gamma v mu plus gamma mu lambda, the covariant derivative nabla sub nu of v super mu, equals the partial derivative partial sub nu of v super mu, plus the connection coefficient capital gamma super mu sub nu lambda times v super lambda. We need to satisfy the why mandate here. Why does this equation look like this?
It's conceptually a subtraction problem. You want the true physical change of the vector, which is that nebula term on the left. To get it, you take the apparent change of the vector as it moves across your coordinates, that's the partial derivative term, and you subtract out the fake change caused by the map itself twisting. That fake change is captured by the connection coefficient, capital gamma. Without gamma, you are blind. You don't know if the vector actually turned or if the space underneath it turned.
That covers parallel transport and the covariant derivative. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to Chapter 2.
Chapter 2. Riemannian Geometry and the Magic of the Levi-Civita Connection. The text says we must define the metric tensor.
The metric tensor is the ultimate ruler of differential geometry. It's usually denoted by a lowercase g. On flat graphing paper, you just use the Pythagorean theorem to find distance. But on a curved, lumpy manifold, the grid lines are stretched differently everywhere you go.
So you need a localized version of the Pythagorean theorem.
Exactly. The infinitesimal distance squared, ds2 equals the metric tensor g sub mu nu times dx super mu times dx super nu. This is using the Einstein summation convention, where those repeated upper and lower indices imply we are summing over all the dimensions. This metric tensor G is a highly customized matrix at every single point in space that tells you exactly how to measure distance there.
That covers the metric tensor. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the two absolute rules of Riemannian geometry.
The text states that Einstein's universe relies on two unbreakable philosophical rules. Rule 1 is metric compatibility.
Mathematically, this is the metric compatibility condition. Nabla lambda guo, the covariant derivative nabla sub lambda of the metric tensor G sub mu nu equals 0.
What does that mean for us practically?
It means the ruler never changes. If you parallel transport the metric tensor G along a path, its intrinsic change is precisely 0. Lengths and angles never change. The scale is absolute. This is the exact rule that Weyl is going to break later, which is why it's so heavily foreshadowed here.
And rule 2 is the torsion-free condition. Gamma lambda mu, capital gamma super lambda sub mu nu equals capital gamma super lambda sub nu mu.
Right. This means the connection is symmetric. If you swap the bottom two indices, it's the exact same value. Conceptually, it means the space might be curved, but it isn't twisted like a corkscrew. If you walk a tiny parallelogram on this space, it perfectly closes. There are no gaps.
That covers the two absolute rules. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the four-step derivation.
This is where the text gets incredibly granular. We are going to derive the Levi-Civita connection. Step 1 is to expand the metric compatibility rule.
We use the product rule for covariant derivatives on that equation that equals 0 and isolate the partial derivative. We get the expanded compatibility equation. Partial lambda gamma, the partial derivative partial sub lambda of g sub mu nu equals capital gamma super rho sub lambda mu times g sub rho nu plus capital gamma super rho sub lambda nu times g sub mu rho.
But the text notes this equation is unsolvable on its own because there are multiple unknown gamma terms.
Exactly. So we move to step 2, which is an index permutation trick. It's absolute mathematical magic. You take that equation and you rotate the indices. Lambda becomes mu becomes nu, and nu becomes lambda. You do this twice, giving you a system of 3 different equations describing the exact same geometry from 3 different dimensional perspectives.
Then step 3, we combine and cancel.
We add the first 2 equations together and we subtract the third. And because we established rule 2, the torsion-free condition, the connection is symmetric. When you add and subtract them, massive portions of the equations perfectly cancel out. All the chaotic unknown variables just vanish.
Leaving us with step 4, multiplying by the inverse metric tensor to isolate the connection. We arrive at the final Levi-Civita formula. Capital gamma super lambda sub mu nu equals 1/2 times the inverse metric tensor g super lambda rho times the quantity. The partial derivative, partial sub mu of g sub nu rho plus the partial derivative partial sub nu of g sub mu rho minus the partial derivative partial sub rho of g sub mu nu.
And we really have to pause on the philosophical takeaway here. Look at that equation. The left side is gamma, the curvature of space. The right side is built entirely out of g, the ruler. The curvature of space is 100% determined by how the ruler changes across space.
Gravity is entirely derived from the unevenness of distance.
It's breathtaking.
That covers the four-step derivation. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the example problem.
The text provides a concrete example to ground this. 2D polar coordinates. Imagine a flat piece of paper, but instead of an XY grid, you draw concentric circles and radial lines.
The paper is flat, but the grid lines are curved. The metric for this space is known. The distance formula is ds2 plus r2 plus r to d theta 2 ds squared equals dr squared plus r squared times d theta squared.
We find the metric tensor matrix, take its inverse, and plug it into our massive Levi-Civita formula to find one specific connection coefficient, the gamma for moving along the theta direction, the arc of the circle.
And the math collapses down to a single result, negative r, negative radius.
Translated into physical reality, what does negative radius mean?
If you are an arrow moving along the arc of a circle, the geometry is actively pulling you inward, toward the center, in the negative radial direction. It's the exact geometric representation of centripetal force. The pure geometry of the grid creates the force.
That covers the example problem. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to Chapter 3.
Chapter 3, Hermann Weyl's Revolution, the relativization of scale. Einstein has just achieved his masterpiece, and Weyl decides to break rule number 1.
He asks the fundamental question, why must the covariant derivative of the metric tensor equal 0? Why is the ruler rigid?
He introduces a scale factor, a gauge transformation. U mu nu x metric tensor g sub mu nu of x maps to g tilde sigma of x, which equals e to the power of 2 sigma of x times g sub mu nu of x. We need to explain the why here. Why use an exponential function e to the power of 2 sigma?
It's a physical safeguard. A physical length cannot be negative. If we all just multiply the ruler by a simple linear variable, it could dip below 0. But the mathematical constant e to the power of anything, even a negative number, always outputs a positive number.
So the ruler can shrink to infinity or grow to infinity, but it never becomes a negative distance.
Exactly. And the reason there is a 2 on APB is simply because the metric tensor g represents distance squared, as we saw in the Pythagorean equation earlier.
That covers the gauge transformation. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the nature of the one form.
Since Weyl broke the rule, the Levi-Civita connection isn't enough anymore. The geometry needs 4 new components to instruct space on how to shrink or grow in the x, y, z, and time directions. This is the one form phi.
And the text makes a critical distinction here between a vector and a one form. A contravariant vector, an arrow with an upper index, is active. It points, it moves.
But a covariant vector, a one form with a lower index, is completely different.
Think of it like a topographic map. It's a collection of contour lines or density gradients spread across spacetime. A one form eats a vector and spits out a number. It calculates exactly how many contour lines your vector arrow crosses.
If you walk parallel to the contour lines, you cross 0 lines. Your ruler stays the same. But if you walk straight up the gradient, you cross many lines, and the one form feeds that high number into the exponential function, shrinking or stretching your ruler rapidly.
Exactly. The one form phi is the instruction manual for scale.
That covers the one form. Have we missed any nuances?
I think we thoroughly unpacked it. Let's move to our final thoughts.
It's amazing to step back and look at what we've covered. We started with the intuitive idea of carrying a wooden ruler. We navigated the sheer complexity of Riemannian manifolds, tangent spaces, and how Einstein locked the scale of reality in place to build gravity.
And then we watched Hermann Weyl completely dismantle that absolute rule. He allowed the ruler's length to change dynamically, and by doing so, the mathematics of electromagnetism naturally fell out of the geometry.
And even though Einstein proved the physical universe doesn't shrink macroscopic rulers like that, Weyl's exact mathematical framework was repurposed a decade later to govern the quantum phase of electrons, giving birth to the modern Standard Model.
It leaves you with such a profound, lingering question. If Hermann Weyl uncovered the hidden mathematical structure of electromagnetism and quantum mechanics simply by questioning the deeply held everyday assumption that length is absolute.
What else are we missing?
Exactly. What other fundamental forces of the universe might be hiding right now behind geometric assumptions we haven't even thought to question yet?
It's a staggering thought. Thank you to everyone for joining us on this incredibly rigorous journey through the foundations of gauge theory. Doing a true deep dive like this, line by line, really reveals the profound architecture of our universe. Keep questioning the obvious assumptions in your own world, and we will catch you on the next deep dive.
All right, welcome to The Explainer. Today, we're going to talk about something kind of wild. How a really simple question, a question just about a ruler, ended up sparking one of the biggest ideas in all of modern physics. It's this idea that maybe, just maybe, the forces that hold our universe together are actually just geometry.
So, picture this. It's 1918. Einstein has just turned physics on its head with his theory of gravity. The dust is still settling. And this physicist, Hermann Weyl, comes along and asks this massive question. He's thinking, could it be that gravity and electromagnetism are really just two sides of the same geometric coin? He had this grand vision, to bring it all together.
So to really get what he was trying to do, and spoiler, his first attempt wasn't quite right, but the idea was genius. We're going to walk through a few things. We'll start with Einstein's universe, talk about this ultimate ruler, then how you navigate curved spacetime. Then we'll get to Weyl's big new rule, see how a force pops out of the geometry, and finally, look at the legacy of gauge theory. All right, let's dive in.
Okay, first up, Einstein's geometric universe. We've got to start here, with the theory that really set the stage for everything that followed: general relativity.
You see, Einstein taught us that gravity isn't some invisible rope pulling things together. Nope, it's just the shape of the universe. Massive things, like the sun, literally bend and warp the fabric of space-time around them. And other things, like Earth, aren't being pulled. They're just rolling along the straightest path they can find in that curved space. It's like a bowling ball on a trampoline. It completely changed the game.
But here's the thing. In this crazy new universe Einstein gave us, where everything's relative and space and time can stretch and warp, there was one thing, just one, that he kept totally fixed, absolutely sacred.
So, in the math Einstein used, it's called Riemannian Geometry. It works like this. As you move through curved spacetime, yeah, your direction can change. That makes sense. But your length? That's always preserved. A 1-meter stick here is exactly the same as a 1-meter stick in the Andromeda Galaxy. It's this core principle called metric compatibility. Think about it. You walk around the globe, your path is curved, but your ruler is always a ruler. It doesn't magically get longer or shorter. That's what everyone just assumed. And this is where Hermann Weyl comes in and just asks this incredibly simple but totally bombshell question. Why? In a universe where everything else is relative, why should the length of a ruler be the only thing that's absolute? It just didn't sit right with him. Why should your yardstick be the one special, protected thing in the whole cosmos? Okay, so to see how Weyl actually tried to break this rule, we gotta get into the weeds just a little bit. We need to understand the tools mathematicians use for navigating a curved world. How do you even compare an arrow pointing that way over here with an arrow pointing that way over there when the ground itself is curved?
The answer is a mathematical idea called a connection. Think of it like the universe's own internal GPS. It's basically a rulebook. It tells you exactly how to carry something, like a vector, just an arrow with a direction and length, along a curved path. It tells you how that arrow's direction has to change from point to point to keep it parallel to where it started. It's the system that accounts for all the twists and turns. Now, Einstein used a very specific rulebook, a very specific connection. It's called the Levi-Citata connection. And what's wild is that this rulebook is baked right into the curvature of space itself. It's not some extra thing you add on. And it has one single absolute prime directive: preserve length. No matter what, the length of your vector cannot change.
And this is where Weyl decides, you know what? It's time to rewrite the rulebook. Let's see what happens if we change that one big rule. His idea was totally radical. He said, forget about length being absolute. What if the measure of length is relative? What if it depends on your location? So a ruler here might be a different length than an identical ruler way over there. The scale, or in his German, the Eiche, which we now call gauge, could be totally local.
So how did he do this mathematically? Well, he started with Einstein's connection, right? The one that only handles direction. Then he just added a new piece to it, a new mathematical object.
And the only job of this new piece was to tell you how much the length of your vector should stretch or shrink as you move it around. It's like adding a new dial to the universe's GPS that controls size. Okay, and this is the part where it gets really mind-blowing. This is where a purely abstract, geometric idea suddenly smacks right into the real world and produces something, well, something real. Because that new piece he added, the one he just made up to let lengths change, it looked familiar, incredibly familiar. When he wrote out the math, he must have just stared at it because he'd seen it before in a totally different part of physics. So check this out. On one hand, you have Weyl's geometric term, this scale connection he invented. Its only job is to describe how length changes from place to place. And on the other hand, you have something physicists already knew all about, the electromagnetic potential, the fundamental field that creates all electricity and magnetism. And it turns out they were the exact same thing. The math was identical. It was a perfect match. This is just incredible. By simply demanding that geometry be a little more flexible, that it have a local scale, a fundamental force of nature, electromagnetism, just popped out of the equations. It wasn't something acting on the stage of spacetime. It was part of the stage, a property of the geometry itself. So you might think, wow, he solved it, unified field theory. Well, not quite. It turns out his specific theory wasn't correct, but, and this is a huge but, the core idea was so brilliant, so powerful, that it completely changed physics anyway. So let's talk about the real legacy. So yeah, his original idea to unify gravity and electromagnetism didn't quite work out. But his central concept of a gauge, this local scale that you can set differently at every point, that was revolutionary. It turns out we just had to apply it to something else. Instead of the length of a ruler, physicists realized it applied to an abstract property in quantum mechanics called phase. But the principle is exactly the same. If you demand that you can change this internal gauge freely at any point in space, you need a force to exist to make the math work. This principle, gauge invariance, is literally the foundation of the standard model of particle physics. It describes not just electromagnetism, but the weak and strong nuclear forces too. It's everything. And that really leaves us with this incredible, profound thought. Weyl's big legacy was changing how we even think about forces. They're not just these random pulls and pushes. They seem to be necessary consequences of symmetry and geometry. It makes you wonder, right? What other parts of our reality, what other forces are just hidden geometry waiting for us to discover them? Something to think about. Thanks for joining me on this one.
You ever hear about an idea that was so brilliant, so elegant, that it completely changed the world, even though it was wrong? Well, that's the story we're getting into today. It's one of the most beautiful and productive mistakes in the entire history of science.
This was the question. A simple, almost obvious question once you hear it, posed by a mathematician named Hermann Weyl. See, back in the early 20th century, physics was all about relativity. But Weyl noticed something everyone else just took for granted. Their rulers. And that one little question, it was about to spark a revolution in how we see the very fabric of the cosmos.
So to really get what Weyl was talking about, we have to picture the world of physics at that time. And that world was basically Einstein's world. He had just turned everything on its head with general relativity. It was this stunning new picture where gravity wasn't a force pulling you down, but was actually the shape, the curvature of space and time itself.
Now, the mathematical language Einstein used to describe all this is called Riemannian geometry. The easiest way to think about it is like this. Imagine you and a friend are at the equator, and you both start walking straight north, perfectly parallel. Because you're on the curved surface of the Earth, your paths will actually bend toward each other, and you'll eventually bump into each other at the North Pole. So, the direction you're moving changes. But, and here's the key, if you were carrying a meter stick, that stick would stay exactly 1 meter long the entire trip. That was the rule.
And that rule, that hidden assumption, is what our protagonist Hermann Weyl decided to poke at. He looked at Einstein's magnificent theory and saw this one little thread hanging off it. In a universe where everything was supposed to be relative, there was this one last, stubborn absolute.
Let's break that down. In Einstein's geometry, if you take an arrow and slide it across a globe, the curved surface makes the arrow turn to follow the curve. That's just what curvature does. But, and this is the part Weyl got stuck on, the arrow itself is supposed to stay the exact same length, always, no matter where it goes.
And this, right here, this is the main event. In one corner, you have Einstein's view, length is sacred. It's absolute. It doesn't change. And in the other corner, You have Weyl asking this incredibly powerful question. Wait a minute, if space can bend and twist direction, why can't it also stretch and shrink length? What if 1 meter here on Earth isn't the same as 1 meter in a galaxy a billion light years away? So to even begin to explore his own question, Weyl had to do something pretty radical. The existing math didn't have an answer. So he invented a whole new kind of geometry, a geometry built on this wild idea that your ruler, your very standard of measurement, could literally change depending on where you are in the universe, a geometry of scale.
Okay, so this slide just nails the difference perfectly. That top animation, that's Einstein's world. See how the arrow moves along the path? It turns, it changes direction, but its size is totally locked in. Now look at the bottom one. That's Weyl's universe. As the arrow moves, it still turns, but it also gets bigger or smaller. Its length is no longer absolute. It actually depends on the path it takes.
Weyl gave this local ruler a name that would go down in history, a gauge. But his really mind-bending idea wasn't just that the gauge could change from one galaxy to another. No, it was that it could be different at every single point in space. It's like every tiny point in the universe has its own private, personal ruler. All right, so Weyl rolls up his sleeves and starts building the mathematical engine for this new gauge geometry. His ultimate goal, his holy grail, was to unite gravity and electromagnetism, the only two forces they knew about back then, into one beautiful geometric idea. He figured if he just followed the pure logic of the math, the physics would reveal itself. He had absolutely no idea what he was about to find.
So, to make this whole thing work, he needed a new piece of math. Think of it as a new rule for the universe. The old rules of geometry explained how an object's direction changes when it moves. Weyl needed to write a new rule to describe how its size changes. And as he was working it all out, just following the logic, deriving these new equations from scratch, something just appeared. The mathematical structure that emerged from his calculations looked familiar. Actually, it looked spookily familiar, like a ghost from a completely different part of physics had just shown up on his page.
And here it is. This is the bombshell. On the left, that's the mathematical field Weyl invented, from pure thought to describe how his geometric ruler changes from point to point. And on the right, that's the math that physicists were already using to describe the force of electromagnetism. They weren't just similar, they were mathematically identical. It was a heart-stopping moment. It seemed like, just by letting rulers stretch, he had derived the laws of electricity and magnetism from pure geometry.
I mean, you can imagine, Weyl was absolutely ecstatic. He published the theory, thinking he'd found the unified theory of everything. But this is the story of a beautiful mistake. And as perfect as it all looked on paper, there was a fatal flaw in the real world. And of all people, it was Einstein who spotted it. He pointed out that if Weyl's theory were true, then the properties of an atom, like its size or the color of light it emits, would depend on its entire history, its journey through space-time. So, two hydrogen atoms that took different paths to get to our telescope would be slightly different. But that's just not what we see. Every single hydrogen atom we've ever observed is a perfect, identical copy of every other one. The theory was beautiful, but it was wrong.
And this, right here, is where the mistake becomes a triumph. This specific theory didn't work. Okay, but the core principle behind it, this idea that a physical law should still work even if you change your local ruler, your gauge, from point to point, that was an idea of pure genius. And that principle got a name: gauge invariance.
So how did this failed idea become the bedrock of modern physics? Well, the story is just incredible. The idea was picked up by the pioneers of quantum mechanics, and they had a clever twist. They said, what if it's not the physical length of a ruler that changes, but an abstract internal property of a quantum particle? And when they applied gauge invariance to that, it worked. It worked perfectly. It turns out that all the fundamental forces of nature, electromagnetism, the weak and strong nuclear forces, are all described by gauge theories.
So think about it. Weyl set out to unify gravity and electromagnetism by making rulers relative. He failed, but in the process, he accidentally discovered the mathematical principle that governs almost everything else in the universe. It really makes you wonder, doesn't it? His beautiful mistake proves that sometimes the wrong road leads you to a far greater truth. What other secrets are just sitting there, waiting for us, hidden in the pure logic of mathematics?
Okay, so what if I told you that the forces holding our universe together aren't really forces at all? What if they're just wrinkles in the very fabric of reality? Today, we are diving into one of the most beautiful and, honestly, accidental discoveries in all of physics. It's a story about one single radical idea that completely changed the game. You see, this was the big, audacious question that physicists were obsessed with in the early 20th century. After a truly game-changing theory turned everything on its head, scientists started to ask, could it be? Could the deepest secrets of reality be hidden not in particles or weird fields, but in pure, elegant mathematical shape? And the person who got this whole ball rolling was, of course, Albert Einstein. Back in 1915, his theory of general relativity wasn't just some new take on gravity. No, it was a total reimagining of the entire cosmos. What he proposed was that gravity and geometry are in fact the exact same thing. The core concept is actually surprisingly simple when you get down to it. Einstein figured out that huge objects, like our sun, literally bend and warp the fabric of space-time around them. So what we feel as gravity is really just our little planet Earth trying to follow the straightest possible path through that now curved space. It's like this incredible cosmic dance, and geometry is calling all the shots. But here's the thing. For all of its mind-bending ideas about relativity, Einstein's theory clung to one single, absolute, completely unquestioned truth. It just assumed that if you had a 1-meter ruler here on Earth, it would still be exactly 1 meter long if you could somehow take it to the Andromeda galaxy. Scale, length, that was fixed. It was constant. It was universal. Now, in the language of math, this has a name. It's called metric compatibility, and it is the absolute bedrock of Einstein's geometry. The easiest way to think about it is like a guarantee. Imagine you're sliding a ruler across a curved map. Sure, the ruler might have to turn and pivot to follow the curve, but the ruler itself, it will never ever stretch or shrink. Its length is sacred. But then, just a few years later in 1918, this brilliant mathematician named Hermann Weyl comes along. He looks at Einstein's masterpiece and asks this profoundly simple yet totally world-shattering question. He basically spotted a philosophical crack in the entire foundation of relativity. Weyl was basically thinking, hang on a second. If time is relative and space is relative, why should length be any different? Why should our standard of measurement, our ruler, be the one thing in the whole universe that's totally immune to change? He suggested that in a truly relative universe, even the length of a meter stick should depend on the journey it takes through space-time. So let's break this down, because this is the crucial difference. In Einstein's universe, if you move a ruler, it only ever changes its direction. But in Weyl's universe, it could change its length too. Suddenly, the rigid absolute ruler was gone. It was replaced by this flexible one whose size literally depended on its history, on its journey. And to describe that, well, that was going to require a whole new kind of geometry. So Weyl gets to work trying to build the mathematics for this wild new idea. He was hoping to unify gravity with the only other force they really knew about back then, electromagnetism. But in trying to do that, he stumbled onto something so much deeper than he ever could have imagined. Here was the problem. All the existing math, Riemannian geometry, was built on that fixed ruler rule. It just assumed lengths never change. So to describe a universe where rulers could stretch and shrink all over the place, Weyl had to invent a completely new mathematical object, basically from scratch. Okay, so let's follow his logic here. First, he just threw out the old rule. He said, let's allow the ruler to stretch. Second, to control how it stretches, he introduced a new field. Think of it like a set of instructions at every single point in space that tells the ruler how to resize itself. But then, when he wrote down the actual math to describe this geometric instruction field, he had this incredible aha moment. The equations he had just cooked up from pure geometry, from this really abstract idea of a flexible ruler, they were a perfect one-to-one match for James Clerk Maxwell's famous equations for electromagnetism. I mean, it was an absolutely jaw-dropping discovery.
And that was the beautiful accident. Just by allowing the scale, or as he called it, the gauge, of geometry to change, he had unintentionally derived the entire mathematical structure of electromagnetism. It suggested something profound, that this force wasn't just acting in space-time, it was a fundamental property of space-time's geometry itself.
Now, as it turns out, Weyl's original unified theory, it was actually wrong for a bunch of other reasons. But that core idea, this new kind of geometric symmetry he had discovered, it was just too powerful to go away. It just needed a new place to live, and it found one in the brand new world of quantum mechanics. And this idea became known as gauge theory. It's this deep principle that says physical laws have to stay the same even if our gauge, our ruler, is changing from one place to the next. And the math showed that for the laws to stay consistent, some new field had to exist to compensate for that change. Well, guess what? That field is the force. It's one of the most incredible insights in all of physics. And why does this all matter to us today? Because Weyl's geometric idea is literally the language we use to describe almost everything. The standard model of particle physics, our best theory of, well, everything, is a gauge theory. It uses this idea to describe not just electromagnetism, but the weak force of radioactive decay and the strong force that holds atoms together. All of them are just consequences of different geometric symmetries. So we're left with this really beautiful, tantalizing thought. Hermann Weyl just asked a simple question: why should a ruler be absolute? And he accidentally found out that fundamental forces are a consequence of geometry. It just makes you wonder, doesn't it? What other deep truths about our universe are hiding out there, not in some giant telescope, but in the pure and elegant world of mathematics?